Ladies and gentlemen, welcome to the March edition of All Space Considered. It is indeed, let me see if I can get this right here, Friday, March 4th, 2022, and we have a very exciting show for you. As always, I'm Dr. David Reitzel, and this show is brought to you by Griffith Observatory, the Department of Recreation and Parks, the City of Los Angeles, and also we like to thank Griffith Observatory Foundation, our nonprofit partner that helps with so much that we do. Joining me tonight, as always, is Chris Butler, Patrick So, Katie Flynn will be here with her pretty pictures, and also a very special guest, Dr. GuhaThakurta, who is my PhD advisor, and he's going to be talking about RR Lyrae stars and the beating heart of our Milky Way. So a very exciting talk there. And also we have a very special end of our show tonight. After All Space Considered, we will be joining Raja on a live Keck run. That's right, a Keck II run coming to you from, well, Hawaii via the Bay Area, via Los Angeles, out to our YouTube stream. So you'll get to eavesdrop and see what it's like to actually observe with the Keck telescope. So that'll be very exciting after our show tonight. After Raja, we'll have our pretty pictures and solar system weather, our sky report with Patrick is always out to launch with Chris Butler. Patrick's going to come back and tell you more about Juno. There's been a couple of more perijovs, and we got some images from the latest one. And I'll close out our show talking about some Saturn aurorae and what we learned about the spin rate of Saturn and why there was some confusion about that early on. But I want to start the show tonight with a brief update about the James Webb Space Telescope. As you know, the Webb was successfully launched, and indeed, it took a selfie picture of its own mirrors that were in the right orientation, they were placed correctly, and then it released its very first image. And that's an image of one star, well, a couple of stars, but one bright star, relatively bright for Webb, and there's 18 different dots there. Well, that was because each of those is an image from a different mirror. Once those mirrors were all aligned, it looked like this, and then they brought them into focus. So they were able to focus each of those mirrors, and it brings them together. As you see, they're making a nice point. Then after they did that, they have to take each of those points and align them into one star. Now that happens a little like this. You can see they have to tilt each of the mirrors until they bring them into making a single star. Now, of course, this was done with the Keck telescope, was the first telescope to do this. And tonight you're going to get to see a Keck run on that. So we might, if we're lucky, get to see something kind of similar to this happen, which will be a lot of fun. And here's that image of that same star. So this is the star with a few fainter ones around it, like I said, but instead of 18 separate stars, we're only seeing one bright one in the middle. So the Webb is indeed working. The instruments are checking out, and we're very, very excited to get more about that in the near future. But now it's time to turn things over to Raja, Dr. GuhaThakurta, and talk about RR Lyrae stars and beating hearts of our Milky Way. Raja, welcome to All Space Considered again. Oh, I think you're muted, Raja. Let's see here. I'm still not hearing him. Yeah, we're not hearing Raja for right now. Let's see if he can get that sorted out.
It's a live show, folks.
And indeed, a live show. We got a lot of moving parts tonight.
Yes.
So I don't know if you need to reset your audio, Raja, or I know you know how Zoom works after all. We've had many a Zoom call with him. Of course, we did a tech check before all this started too. Well, while he works on that, I will say what you're looking at here is an image of the two Keck telescopes on top of Mauna Kea. Those telescopes are on top of the nearly 14,000 foot mountain, and you're looking out across the ocean, and you can see why they're in such a great location to observe. Oftentimes you're up above those clouds, and also the air is very smooth. As it comes in from the ocean, there's nothing else to disturb it and make it sort of turbulent, which causes the stars to twinkle. So I do see, Raja, that you're muted on Zoom right now. And there you're unmuted supposedly, but we still don't hear you. So I don't know if it's your headphones.
You know, some of the audience may not know this. When we say a Keck run in the Keck telescopes, we're going to get a chance here to eavesdrop basically on operation of one of the largest telescopes in the world. A very important instrument. This is a big deal.
Yeah, it really is. And Raja's going to tell us more about that. I think I did hear you when your headphones were unplugged, Raja. We're still not hearing you through the microphone on them, though, for some reason. No, we still don't hear you. You might want to log out and log back into the Zoom call. It might be the best way to try it. We were hearing him at 6 o'clock. But like Chris said, indeed, tonight, as part of a program called Shadow the Scientists, we're going to, after All Space Considered wraps up at 9 p.m., we're going to tune in to his Zoom call that they offer the live view of what's happening to the instruments, how the scientist is operating it, what images they're getting, what spectra they're getting. And we'll get to watch all that happen live. This was a program that was started to let students be able to see what's happening. And indeed, there might be some students in their Zoom call, but we're just going to stream the main images that are coming from there. As we wait for Raja to come back, I can tell you a little bit about our own program tonight and a little bit about what's happening. The Griffith Observatory Foundation, like I said, does support much of what we do. And you'll see the fundraiser that's down below there. All the donations that we get there go straight to our foundation, which then supports our programming, which can be really terrific. In addition, our foundation is offering tickets and things like that for special events to their members. And tonight we actually have a giveaway of a couple of tickets for a foundation event that's going to happen in our planetarium. And stay tuned for that giveaway. So Raja, did you manage to get reconnected here?
I'm back. Can you hear me now?
Back. We can hear him finally. Welcome, Raja. It's so good to hear you.
So sorry for this drama here. Totally unnecessary. So I had to log out of Zoom and back in. But I'm back.
Well, that's what Zoom does to us sometimes. It'll work perfectly, and then the next thing you know, it doesn't. But we're just glad to have you here tonight, and take it from here. If you'd like to, tell us all about what you're going to be doing with RR Lyrae stars and what we're going to get to see tonight.
Thank you. So it's a real pleasure and an honor to be on All Space Considered. This is my third time on the show, and the first two times were in person. This is my first time on virtually. So I'm going to talk about RR Lyrae, the beating hearts of our Milky Way. Our Milky Way has many hearts, and we have discovered 200 of these hearts in our Milky Way, but others have found even more. And I'm going to talk about them in just a few minutes. Just a quick word about myself. I teach astronomy, and I have the misfortune of being the department chair at the University of California, Santa Cruz, Department of Astronomy and Astrophysics. My solitary sentence in this role will be over in a year and a few months. But I'll say a little bit about the science internship program that I help run later on in this segment. All right, so I'm going to talk about RR Lyrae, how we use them to study the structure of the Milky Way, and how our study and others like it are challenging Immanuel Kant's idea that galaxies are island universes. So let's take a look at what RR Lyrae look like. So here is a beautiful image put together by the OGLE team, the OGLE group that was based in Poland. And they took a series of images of a section of a globular cluster called M3, Messier 3. And if you look closely at this image, I'm going to turn my laser pointer on and put it right next to one of these beating hearts, right to the left of my laser pointer. To the left of my laser pointer, you see one of these beating hearts. And they are pulsing in brightness. It's a time lapse and it's looping. So actually, even if it didn't loop, the stars loop. That's the whole point of it, is they go up and down in brightness. There's one right next to my laser pointer there. There's another one up here next to my laser pointer again. They're all over, actually. There's one in the upper right, just above my laser pointer. And you'll notice a couple of things. You'll notice they go up and down in brightness. They're not all in sync. Some are going up while others are going down. But they all look roughly the same brightness. And I'll come back to that in a moment. They look slightly bluer than the rest of the stars in the globular cluster. Like the really bright stars look reddish orange. These stars look slightly bluish or bluish white. And they all look like their average brightness is about the same. Okay, so I'm going to turn my laser pointer off now. And so what makes RR Lyrae useful to study galaxies or study the Milky Way, galactic studies? Two things. The first of those is they're easily identifiable. It's like looking out of your window in a busy cityscape. Say you're in a skyscraper in Manhattan and you look out of your window, there are all these lights all through the city. And it's hard to tell how far away each of these lights is. And it's hard to know what type of light is shining at you, except you notice that a few of them are pulsing with this very characteristic pattern, or this heartbeat pattern. And you notice that they're pulsing, and you notice that there are some of these pulsing stars right in your neighboring skyscraper that's across the street from you. You know the distance to that skyscraper, and you find that all of the ones in your neighboring skyscraper have exactly the same time average brightness. So not only do they have an easily identifiable so-called heartbeat of brightness variations with time, periodic, and that's what I mean by repeating. And they're also standard candles. That is, if you average their brightness over time, each RR Lyrae's average brightness is like the other. So their brightness variations look something like this. You see time running on the x-axis and brightness running on the y-axis. This is an example of a single RR Lyrae being observed in a single filter, going up and down in brightness. You can see the rise time is very sharp. The fall time is somewhat slower, sort of like an EKG, and that's why heart beats. And here are some of our own measurements. This is from Yuting Feng's work. And we've made measurements of the same star. Now, not the same star as the one on the left, but a given star in 4 different filters, UGIZ, so ultraviolet light, green light, far red, and the beginning of the infrared. So, and you can see that these stars, the pulse is more extreme in the ultraviolet than it is in, say, red light. That's another characteristic feature of these things. Now, if we look at something called a Hertzsprung-Russell diagram or a color magnitude diagram, you can see that the RR Lyrae land somewhere there. They are quite a bit to the left of the brightest stars in the globular cluster, but you can see that they form sort of a horizontal sequence. So it's luminosity on the y-axis, so how luminous the star is, and temperature on the x-axis, temperature increasing to the left. So you can see these are hotter than the brightest stars in the globular cluster, but they also all have the same time average brightness. This is what I mean by standard candles. Now, before I talk a little bit more about RR Lyrae in our own study, let's take a look at our Milky Way galaxy. Okay, so here's our Milky Way, and I'm going to show you a time-lapse movie of the Milky Way. This is a beautiful time-lapse taken by John Rockman. He just used a digital SLR. He set it up in a game park in Kenya, took a series of half-minute exposures and stitched them together into a time-lapse. What I'll do is I'll get rid of the label so you can focus your attention on the movie itself. So there we go. You can see the rotation of the Earth. The sky gets darker. You see some shooting stars, some lightning, clouds. And of course, this apparent sweeping of our Milky Way galaxy across our sky is a result of the fact that we're observing it from the Earth, a rotating Earth. So this is our grand home, our Milky Way. And there's been a lot of beautiful computer simulations that have been carried out by people who specialize in understanding how dark matter works in the universe. They use supercomputers to do these simulations. I'm going to show you one of these simulations called the Illustris simulation. And what you see in bluish white is a representation of the dark matter particles that make up a typical galaxy. And what you're seeing here, as time goes forward, you can see time in billions of years counting up since the Big Bang in the lower left of the frame. But as time counts up, the rotation is just so you can get a 3D sense of the structure of dark matter particles in space. The universe isn't rotating at anything like this rate, but we are changing our perspective so you can see the buildup of dark matter in the halo of a galaxy the size of our Milky Way. So this is you're seeing in simulation time, in computer time, highly sped up because billions of years are going by in a matter of seconds of our time. You can see that stars are exploding, and the greenish and the red and orange are no longer dark matter. Now we're talking about gas and stars that you're seeing in the different colors. The blue is the dark matter. The blue that you were seeing earlier is the dark matter. So galaxies are supposed to be exciting according to the people who build computer simulations. And so we want to go out and look for this kind of structure in our Milky Way galaxy. Now, of course, we are stuck inside our Milky Way galaxy, so we are sort of studying it from the inside. So we want to keep that in mind. So what I'm going to show you next is an artist's impression of what the Milky Way would look like if it were viewed from the outside. That is, if we had a long enough selfie stick, we could take a picture of the Milky Way. This is what it might look like. I'm going to stop the computer simulation. The illustrative simulation is just beautiful. So here's what our Milky Way might look like from the outside. It says artist's impression because we've never really taken photographs like this. The selfie stick would need to be too long. And on this scale, the center of our Milky Way is at the center of this frame. But our sun, which is symbolized here by this symbol, not shown to scale, needless to say, is located about 25,000 light years from the center of our Milky Way galaxy. That's our sun and solar system. And by the way, if you try to put a picture of our solar system and our sun in this picture, on this scale, the entire solar system would be smaller than a single pixel. So that's why the sun is being shown as a symbol and not to scale. Okay. Now let's take this Milky Way galaxy and let's remove these labels and let's put the galaxy sort of on its edge and let's shrink it. And on this scale, what we have done, and I'll explain who we is in a moment, is we've found RR Lyrae that are located very far away from the center of our Milky Way. And how far, you ask? It's this far. On this scale, instead of 25,000 light years, which is the distance of the sun from the center of the Milky Way, this pizza slice that you see here, every dot is an RR Lyrae star that we found. And this is the discovery of some of the most distant known stars in the Milky Way. They are up to 1 million light years away. So roughly 40 times the distance of the sun and solar system from the center of the Milky Way. Now, this is the work of a PhD student at UC Santa Cruz who's actually currently calibrating the Keck telescope, getting ready for tonight's observation. His name is Yuting Feng. And also the work of a former UCSC PhD student. She is currently a postdoc in New York at the Flatiron Institute. This is Emily Cunningham. Emily finished her PhD in 2019. And Yuting and Emily and Eric, whose picture I don't have here, and I, the four of us, are working together. It's one graduate student, one postdoc, and two faculty are collaborating on this project on Keck tonight. Now, we found these very distant stars in the Milky Way, and I want to explain that this is not unique to the Milky Way. We are finding stars that are so far away that it's about halfway to our nearest galaxy, Andromeda. And Andromeda seems to have stars located that are about halfway of the distance from Andromeda to us. And so talking about Andromeda, this is a digital mosaic that my students and I made in the early 90s. My undergraduate students at Princeton and my grad student at Santa Cruz, Phil Choi and Andreas Berlind, you'll see their names at the bottom. They helped put together this digital mosaic of Andromeda. And I say this, there's 4 versions of it at different contrast levels. And each mosaic consists of 57 images in blue and infrared light. This was the first digital mosaic anyone had made of Andromeda. We're talking about 30 years ago. Now, I'm going to remove all but one of them. And we're going to shrink this in size so we can see far away from Andromeda's disk. So there we've shrunk it. And there is this beautiful survey called PANDAS, which is a survey run out of a group in Canada that looked at the density of stars around Andromeda, and the grayscale, the inverted grayscale, the dark on light, is a map of stars around Andromeda. Now, our group, the SPLASH survey, went out and measured the density of stars as a function of distance from Andromeda's center using the Keck telescope, and that's what you see in this graph here. So on the x-axis is distance from Andromeda. I'll give you that distance in light years in just a moment. On the y-axis is the density of stars as we march further and further away. So Andromeda has stars going out to nearly 1 million light years from its center as well, not just the Milky Way. And this was the work of the initial work on the outer halo of Andromeda was the work of Carrie Gilbert. She was the PhD student at UC Santa Cruz at the time. And I'm currently working with Alice Deason, a former postdoc at UC Santa Cruz, who's a professor at Durham University, who is studying the very outskirts of the Andromeda galaxy, with Emily and me. Now, the person who got me started on this road is none other than your fairy, Dr. David Reitzel, because David's PhD thesis was the first to get spectra of stars in the halo of Andromeda in numbers that no one had done before. And this, David, you and I started this work, I still remember, on October 2nd, 1996. I actually have the telescope proposal from that observing run. And October 2nd and October 3rd were the first two nights we had for this project. They were the second and third nights of operation of the Keck II telescope. And we were using, at that time, the LRIS spectrograph to do this work. I think it was the Keck II telescope that LRIS was on at the time.
Yeah.
So a nod to David for really getting me started on this road. So the picture that's starting to emerge is in galaxies like Andromeda, the Milky Way. The stars go out very, very far from the center of the galaxy, practically out to the neighboring galaxies. And this challenges a very important notion that was put forth 250 years ago by a philosopher named Immanuel Kant. He put this forward almost exactly 250 years ago, 1755. Kant was a philosopher, and his perspective of what was then called island universes, what we now call galaxies, was that there are these islands of light separated by vast amounts of empty space. Now, Kant's idea was absolutely brilliant because it was really in the realm of philosophy rather than science at the time. And it couldn't be tested very easily because we didn't have powerful enough telescopes, and his ideas sort of died out and wasn't very popular in terms of being discussed by the community for nearly 150 years, until the early 1900s came along, and two scientists, Curtis and Shapley, had what is now a famous debate. This is now 100 years ago, 1920, a famous debate about the ultimate nature of our galaxy. So Curtis was of the opinion that these islands that we see are far away from us and are just like the Milky Way. And Shapley was of the opinion that those islands were inside our Milky Way. And so they had this debate, and as data collection improved and measurements improved, it turns out that Curtis was right, that these nebulae in the distance were about the size of the Milky Way. They were just very far away. That's why they looked small to us. And Shapley, who thought they were much closer inside our Milky Way, was mostly wrong. I say mostly because there are stars, there are galaxies close to us, like the Large and Small Magellanic Cloud, that are inside the halo of our own galaxy. So there are some galaxies that are smaller and inside our own galaxy's halo, but most of them are far away. And so for our studies of the Milky Way halo, we use the twin Keck telescopes on Mauna Kea, and we use the Lick telescope at Mount Hamilton in California, very close to where I live here in Northern California. So here are the telescopes in question. The two Keck telescopes on Mauna Kea shown on in the upper left, and the Lick telescope with its famous sodium laser shining out. This is the Shane 3-meter telescope. 3 meters is the diameter of the Shane telescope mirror. It's a single mirror in the Lick telescope. And as Dr. Reitzel mentioned, each of the Keck telescopes is segmented. Each of them has 36 segments. Each segment is the size of a human being. Each of the Keck telescope mirrors, with all the segments put together, is about 10 meters in diameter. So 10 meters for the for the telescope on the left. Sorry, I'm just going to go back. 10 meters the mirror diameter for the Keck telescopes, and 3 meters for the Lick telescope. Now, because of the pandemic, the telescopes were actually shut down in the summer of 2020 when the pandemic first really hit the U.S. and mainland of the U.S. and Hawaii. And then in sort of the late summer, they started opening it up, but they said, you can't come to the observatory. we're going to start something called pajama mode, where you don't have to get into your street clothes. You can be in your jammies, but you can still use the telescope from your computer. So we're going to do that tonight. I'm not going out to Hawaii. I'm sitting at home in Northern California. My graduate student is sitting at home in Santa Cruz, and we're going to use the Keck telescope. And tonight, what we're going to do is we're going to use the Keck II telescope, the 10-meter, one of the two 10-meter telescopes pictured above, and the ESI spectrograph. We're going to take obtain spectra of individual RR Lyrae stars that are located up to about 500,000 light years away. Not the most distant ones, those are too faint for us to get spectra, but about halfway out to the most distant ones, we're going to get spectra. So we can measure their Doppler shift from the spectrum and measure how fast they're moving in response to the gravity, not just of the Milky Way, but one of these neighboring galaxies that we're in the process of cannibalizing, the Large Magellanic Cloud. So we're looking at the effect of the Large Magellanic Cloud on our own Milky Way, the gravitational effect. And because we're doing this through Zoom, I mean, Yuting and I are going to connect through Zoom, Eric's going to connect through Zoom, we decided we would open up our Zoom windows, virtual windows, to other people. And this is an initiative called Shadow the Scientist. We're going to invite this audience here to come watch us work. And we've invited a worldwide audience to come and do this. Now, in the next few minutes, and this is really the last thing I want to say here, in the next few minutes, I want to talk about how Shadow the Scientist fits in to a set of initiatives we're running out of UC Santa Cruz that we call CREST. C-R-E-S-T stands for Creating Equity in STEAM. We are working towards creating equity in STEAM. We don't hope to achieve that in one person's lifetime or through one organization's efforts. But what we're trying to do is the horizontal words in this crossword puzzle are what we're trying to achieve. We're trying to create equity in STEAM. STEAM stands for science, technology, engineering, arts, and math. And the way we're trying to create equity is by engaging young people in critical thinking in the context of open-ended research under the close mentorship of world experts. And I want to emphasize why I personally feel this is important. We're in the middle of a pandemic, as we all know. We might be in the late stages of a biological pandemic, but there's another kind of pandemic that's been raging through the world for a little bit longer than COVID-19, and that's an information pandemic. And we saw this in the politics of the world, in the politics of the US, a pandemic in which evidence-based information was not being given its due weight. The loudest voices were being heard, not necessarily those who are the most expert in a particular area. The notion of that there is something called expertise was really at risk. And I would say was at risk, it still is at risk. With COVID-19, you start by vaccinating the elderly because they're most at health risk. With the information pandemic, you start by vaccinating the youngest people because they're going to live with this for the longest. And these efforts that we're doing, creating equity in STEAM, engaging young people in critical thinking through Shadow the Scientist and other initiatives, is really the vaccination for the information, one of the many vaccinations for this information pandemic that we find ourselves in the grip of. So it's a step-by-step process. We first want to take young people, and have them dip their toes in the water of STEAM. And that's what Shadow the Scientist is. It's an hour of a young person's time to say, let's see if this activity feels right. Who are the people involved in this activity? It's like saying, before you plunge into the ocean, you want to dip your toe in the water and see if the water temperature feels right. And more importantly, if the people who are already in the water feel like the people you want to hang out with. Okay, so this is what Shadow the Scientist is. It's dipping one's toe, allowing people to dip their toes in the water, especially young people, young children, educators. Once you know that, once you've done that and you say, yeah, this is for me, I want to do some more, you want to learn the swim strokes. And we do this through something called Python and Research, PR, a tutorial that my students and I started, where we teach some of the techniques that you need to use in science today. Python is a very important programming language in science today, but we teach this in the context of research. And one of my colleagues in biomolecular engineering, Gio Chavez, teaches the programming language R in the context of research in computational biology. The first one, PR, is set in the context of astronomy research. The second one, computational biology research. And this is learning the swim strokes. Then you want to take the deep dive, and we run a program at Santa Cruz, a summer-long program. Now we're talking about a young person committing 100 hours or a couple of hundred hours of their entire summer to this. My wonderful colleague at Arizona State University, Annette Lee, she and I collaborate on something called We Are Stardust, where we bring in, as Annette describes it, two-eyed seeing, where a child looks at the universe through a Western lens, through one eye, looks through an indigenous lens with the other eye, and combines those two, looks through both eyes for the benefit of all. So combines sort of three strands in a braid: the science story, the cultural story, and the personal story. And after you take a plunge like this, you can take part in something called the Global Sphere Network, which is a community of practice of people who engage young people in research. So it's sort of a pay it forward attitude. We have an alumni buddies program. We follow the trajectories of students who go through this. We engage teachers in the science internship program. That's what TSIP is. We have a peer-to-peer college and career network. That's what P2C2N is. And then we involve community college students in the science internship program. Now, that's all the slides I have. And so I would love to see if there's any time for questions.
Well, I have some questions, although we're going to back up off this slide. But Raja, I do have a couple of questions. So you were saying that Kant's view was that there were island universes, but the research that we've been doing, that we kicked off together and that's been happening, suggests that they're not quite also separate, that there's connections between everything. So how far out do these connections go? Is this something that is universe-wide, or where would you draw the line to say that we're no longer influencing each other?
That's a great question, David. I think it is universe-wide. I don't think it's unique to the Milky Way and Andromeda galaxies. I do believe that these boundaries of galaxies are very interesting. What does it mean for one galaxy to have ended and another one to have started? And the way you measure this is by measuring the motion of stars. If there's a particular star that's in orbit around the Milky Way, it's fair to call that a member of the Milky Way, influenced primarily by the gravity of the Milky Way. If you find something that's orbiting Andromeda, it's fair to call it a member of Andromeda. It's when you find stars that have been orphaned from both or are really in this tug of war between the two that you've defined the boundary. So that's the holy grail of this work. We haven't reached that yet.
Okay, interesting. So you also mentioned that we're cannibalizing galaxies. And what's the evidence for that? What can you tell our audience about what you found?
I'll talk about not just what we've found, but what other astronomers have found. We can clearly see galaxies that are being ripped apart by one galaxy being ripped apart by the gravity of the other. So there is the Sagittarius galaxy that's being ripped apart by the Milky Way. And the reason galaxies get ripped is because the near end gets pulled harder than the far end and they stretch out. And once that happens, it's sort of a runaway process. So the Large Magellanic Cloud is something that's being cannibalized by the Milky Way, the Small Magellanic Cloud as well. Those are three examples of galaxies, one that is in the process of being digested, the Sagittarius one, but the other two are they're just coming into our, the Milky Way's alimentary canal, so to speak.
Okay, very, very interesting. One of our audience members in the YouTube chat wanted to know if any stars could be transferred from one galaxy to another, say from Andromeda to the Milky Way.
Absolutely. Not only can stars be transferred from one galaxy to another, what happens more commonly is when galaxies collide, their identities get lost as separate galaxies, and stars that used to orbit galaxy A, one set of stars used to orbit galaxy A, another set of stars used to orbit galaxy B. When the two galaxies come together, both sets of stars start orbiting a common center, and that's exactly what happens when galaxies collide. So the Large Magellanic Cloud is affecting the trajectories and motion of some of the stars that are, you could call them Milky Way stars, but they're actually being affected by the Large Magellanic Cloud as well. That's exactly what we're trying to study tonight, actually.
Okay, fascinating. Another quick question, and I'll see if Chris or Patrick has any questions. Why did you make Curtis Darth Vader in your Curtis Shapley poster?
I didn't. Whoever put that poster together did. And Darth Vader was correct in this case. Curtis was right.
Well, eventually he was correct. He did turn. And anyway, we don't need to get to no spoilers of Star Wars in this. So.
Right. The interesting thing is they were both correct in that debate, right? So is Shapley right when he says some galaxies are inside the Milky Way? Absolutely, but not all galaxies. Curtis, I think, was more right than Shapley. Most galaxies are outside the influence of the Milky Way, and only a few are inside.
One of our audience members wants to know, are RR Lyrae stars uniquely likely to be found in the outer regions of galaxies? So are they only found out there, or would you find them in the disk as well?
That's a great question. We are, from what we understand of, collectively as an astronomy community, what people understand of RR Lyrae stars is they have to be relatively chemically anemic. They have to be stars that are comparable in mass to the sun, but much more chemically anemic than the sun. Let's say roughly 30 times more anemic. What I mean by anemic, I mean the iron to hydrogen ratio in the sun, whatever that number is, in these stars, in RR Lyrae stars, that ratio is 30 times lower. The ratio of iron to hydrogen is roughly a factor of 30 lower. So stars have to be chemically anemic, and chemically anemic stars are actually very common in the Milky Way. They're more common than sun-like stars. The sun is unusually metal rich or iron rich. That's one condition. The second is the star has to evolve off the main sequence. Right now the sun is on the main sequence. It's converting hydrogen to helium in its core. It has to finish up using all the hydrogen in its core, become a red giant, and then it has to ignite helium in its core for it to become something called a horizontal branch star. And an RR Lyrae is a specific subclass of horizontal branch stars, where the chemical abundance is just right, not too low, not too high.
Gotcha. So by the way, for folks that are confused of how you could end up with anemic stars, remember the universe started out mostly hydrogen, some helium, a little bit of lithium, and it was the stars that forged the heavier elements in supernovae explosions. Also collisions of stars as well. White dwarfs colliding will make a supernova explosion as well. But it takes those events to create the heavy elements. And in fact, it's the white dwarfs colliding that make a little bit more of the iron. So that iron tends to lag a little bit some of the other elements. So it's a very complicated story, but in general, stars that are made in a galaxy later in that galaxy's life will have more iron in them. So that our own sun was several generations down into the Milky Way's creation of stars. We were not one of the first stars formed in the Milky Way. Let's see here. We have got another question from our audience. And then Chris, if you have any, or Patrick, certainly join in. But somebody wants to know that when the Milky Way and Andromeda collide, will our sun or any other stars be flung outside the galaxies?
Absolutely. Stars will be flung outside our galaxies. It's hard to predict exactly which stars, but stars in the outskirts of these galaxies are more likely to be lost. Stars that are already tenuous in terms of their gravitational attraction to each galaxy, to Andromeda or Milky Way, those are most likely to be lost. It's unlikely for the sun to get orphaned like this. Galaxy collisions are like corporate mergers, so some people get laid off, and that makes the remaining organization even stronger. That's what happens. And literally, the stars that get orphaned carry away energy, allowing the rest of the system to settle into one galaxy. So they actually, the energy they take away is really important for the collision and merger process.
How about planets? Will they be safe if we could live long enough to see this happen on Earth? If
absolutely, yeah,
kill us in the process, let's assume. Would Earth be in any danger?
Not really, because the connection between stars and planets is the gravitational force is way stronger than the forces that stars experience during galactic collisions. So it's very unlikely for a star to come close enough to disrupt the solar system. Not in the Andromeda collision. There'll be other things that'll kill us long before that. Politicians most likely, but the sun bloating up into a red giant is going to be the thing that will fry the Earth, not the Andromeda collision.
Yeah, indeed. Chris, Patrick, do you have anything you'd like to know?
I have a question.
Yeah.
Oh, go ahead, Chris.
Yeah, this is really fascinating. I mean, as someone who's interested in astronomy, I've always thought, sure, there are some stars out there between galaxies. Some will get ejected. Sure, I know that. But when you showed that chord looking out, that angle looking out from us, the number of RR Lyrae stars you've found knocked me back. And the reason for that is I know RR Lyrae stars are relatively bright, much brighter than our sun. My question is, what else is out there as far as the population? Does it look like the population of our galaxy? Meaning, the yellow dwarfs, the red dwarfs. There could be a huge number of dimmer stars out there in this population, and you're just looking at the brightest ones you can see from here. Do I have that right?
You have that right, Chris. The RR Lyrae are not the absolute brightest stars that are out there. Alice is leading a project to look for very distant red giants. Those are, the problem with red giants is there's a superposition problem. You have foreground red dwarfs that can masquerade as distant giants. So, but we're using the Lick telescope to look for distant giants that would be the comparable distance to these RR Lyrae, but even more luminous than for sun-like stars at these distances would be very difficult to find because they're so faint. I mean, this is already challenging to find RR Lyrae.
Yeah, I'm amazed. This is really something.
Now, I was wondering, Roger, what is the nature of the pulsation? What is the mechanism associated with it, and what is the period of the pulsation of RR Lyrae stars? Are they they have a regular period?
They do, Patrick. So RR Lyrae come in two flavors. The one flavor is called RRAB, and that's one flavor. The other kind is called RRC. The RRAB stars have time periods between half a day and 3/4 of a day, so 12 to 18 hours. There's some range. Some are even more than that. But most of them are in that period range. RRCs have shorter periods. They're between 1/4 of a day, 6 hours, to maybe 10 hours. 6. So, and they do have a range of periods. But your first question was, what causes this? And a star, in a way, is a static nuclear bomb. The nuclear fusion that's trying to push everything outwards, the tremendous energy of nuclear fusion that's causing the star to shine is also trying to push everything outward. Radiation pressure driving the star outward is balancing its gravity. It's just balancing its gravity. And what happens in certain phases of stellar evolution is stars hit what is called an instability strip, where while these two things are balanced, they reach a dynamic of balance instead of a static balance. They oscillate about, it's like having a pendulum is a beautiful balance between the Earth's gravity and the tension of the wire that's holding the ball. It could be in static equilibrium if the pendulum is not swinging, but it could also be in dynamic equilibrium if the pendulum is swinging. So stars go through the swinging of the pendulum phase, which is this oscillation where the nuclear fusion, when it's winning, the star expands, and then gravity reins that in, it starts to compress. And so it goes through this very, very strictly periodic cycle.
Very, very interesting. Well, once again, thank you so much for joining us tonight, Raja. It's been a real pleasure hearing about what you're doing with RR Lyrae stars, about how more evidence that Andromeda and the Milky Way are actually probably joined by a bridge of stars. And you keep pushing this boundary out from the Milky Way and then out from Andromeda. And someday we'll hear that the two have, joined in the middle. Kind of like the Transcontinental Railroad. This is the transgalactic star trails, I guess, that are joining between these. And it's just fascinating to know that galaxies are no longer these separate islands, that they really do influence one another, and the universe is connected by these webs of dark matter that just really, we've learned so much in the past decades that it's just fascinating to hear all this work. So thank you again for joining us. And folks, like we've been saying, when All Space Considered ends tonight at 9 p.m., we will get a chance to join Raja on his Keck run, Keck II, with the ESI spectrograph, where he's actually getting spectra of these RR Lyrae, and you'll get to see what it's like to be on an observing run. Now, you don't need to go anywhere. You could just stay right here on YouTube and watch our stream. We're going to stream it right along with the end of our program. So stay tuned for that, and certainly enjoy the program. And Raja, we'll see you in about 45 minutes or so.
Thank you so much for having me, David, and thank you for getting me started on this bridge of dreams to Andromeda. Thank you.
Well, it's just you're very welcome, and thank you, of course, for letting me take part in that. It was just a wonderful time we had, and I still Still remember back to those good times? And, it's kind of special that you're on Keck II, that same telescope that we got those first spectra of those red giants in Andromeda tonight. So it's kind of coming full circle in a way. So it's really neat. So thank you again.
Take care.
Well, folks, I want to talk about very briefly an opportunity that you have to come to a Griffith Observatory Foundation event called Above. It's a night gallery, The Stars of Spring. Indeed, this is a planetarium show. It's going to be given by our very own director, Griffith Observatory director, Dr. Krupp. And the show is sold out. You needed to be a foundation member in order to get tickets. They offered them to all their members. They were grabbed right away. But tonight, we have an opportunity for you to get a pair of tickets to this show. The show is, oh gosh, we didn't give the date of it up there, but it's March 14th. And you'll be able to come up to Griffith Observatory and see a live planetarium show from the Samuel Ocean Planetarium. But you can get these tickets if you're the first person to tweet at us. So you need to have a Twitter account, and you can go create one right now. And if you send us a message at All Space Considered, but the considered has no vowels in it, but you can find us there if you search for All Space Considered. But tweet at us the date of the vernal equinox as it occurs here in Los Angeles. So when is the first day of Northern Hemisphere spring? What is the date of that? So send us a message on Twitter of when that is, and you can win 2 tickets to this wonderful planetarium show that we're going to have, talking about the stars of spring. So, but right now we're going to move on to our next section of the show. Katie, there you are. So nice to see you. And Katie's going to show us some beautiful pictures, some of them astronomical, and well, some of them just beautiful artwork. So Katie, welcome.
Thank you. Well, our first pictures are actually drawings from our guest Raja. So I will pull those up here. So just some beautiful, beautiful images. He's also an artist, so that's so wonderful.
He sure is.
Yeah. And in fact, he just recently had an art show up in the Bay Area. So astronomer and artist, and just overall a wonderful human being. So it's great to see these.
I won't be able to leave my room. My head is swelling with so thank you for indulging my art here. Thank you.
Of course. This is,
well, there's an A in STEAM, and that's for art.
That's correct. This is your niece and daughter. So lovely.
Yeah. Oh, jealous artist here. Oh, that's amazing.
Yeah, oil on canvas, just stunning.
So thank you so much, Raja, for sharing these with us.
Thank you.
Such beautiful images. So this image is Venus and Mars. This is taken by Dario Giannoble. He posted this on March 3rd, and you can also see the Milky Way. That one was from Italy. And this is a gorgeous image from Blake Estes. It's a mosaic of Rho Ophiuchi. And the star was taken by our telescope demonstrator, Anthony Perkic. This is Vega. And this image was actually taken by Patrick So. You can see Orion there, kind of in the middle of the screen, setting in the west over the mountains, and to the left, the bright star Sirius visible. And on to some cloud appreciation pictures. These are iridescent clouds. This one was taken by Phil Plate, and he posted this on February 5th. And then a beautiful sun halo. This is by museum guide David Pinsky. He took this from Griffith Observatory on the 20th of February. And I love this one. This is a time lapse. I edited this one down to 15 seconds. This is over New York City, a cold front going through. This is by Alexander Krivenishev on February 18th. He takes these from New Jersey. And this gigantic jet you may notice from previous months of the show, showing again because in the middle there you can see that enhanced green color. That's actually called a green ghost, and it was discovered not too long ago in 2019, and for the first time ever, it was spotted from a jet, and that this jet in particular. And green ghosts are clouds of oxygen atoms that are about 90 to 95 kilometers above Earth's surface. And the green glow, the atoms glow green at a specific wavelength. They're excited by electric fields from thunderstorms. So coincidentally, these are the exact same wavelength of oxygen emission that give aurora their green color. So they say, in a sense, auroras are for sprites and now gigantic jets too. They are auroras for sprites and now gigantic jets too. And on to some space weather. On February 3rd, SpaceX launched 49 Starlink satellites. And just a few days prior to that, this is from January 30th. This is a coronal mass ejection that erupted from the sun. And following that, there was a powerful M-class solar flare that headed toward Earth. And M-class solar flares are medium-sized space weather that can cause temporary radial blackouts on Earth. And here we'll just show the associated sunspot with this. And the interesting thing about the sunspot is that it's one of the largest active regions in our current solar cycle. And this 2936 quadrupled in size in just 48 hours. So unfortunately, there was a geomagnetic storm from all of that caused the Starlink satellites to fall out of orbit. And this is cut down. You can see the full version on YouTube, but this is from February 7th over Puerto Rico of them coming back into Earth's atmosphere. All right, and then on February 16th, this is a huge coronal mass ejection that actually occurred on the far side of the sun. And it is the only the second far side active region this size since September of 2017. But because it was on the far side of the sun, it was heading away from Earth. And since there are no spacecraft on the far side of the sun with X-ray centers, there's no way to know how strong it was, but the best guess was that it was an X-class flare, which is the most intense flare. And also, Lucas Giuliano, who's a solar scientist at the Harvard Smithsonian Center for Astrophysics, believes that the sunspot that caused this was also the sunspot that caused the geomagnetic storm that knocked out those Starlink satellites, AR 2936. And just to end the pretty pictures and space weather segment with some beautiful aurora. This was taken by Göran Strand, who's in Sweden. And I love this one because right in the center there, you can see Ursa Major, the Big Dipper. The beautiful one.
Yeah, really neat.
Great.
Well, thank you, Katie, for those beautiful pictures. And folks, I love that folks in our YouTube chat have been giving away the answer. In fact, it was none other than our very own Tony Cook. Anthony Cook is in our chat. So thank you for joining us tonight, Tony. It's always a pleasure.
Hey, Tony.
We miss you very much, of course. And he gave away the answer. So if folks want to know the answer, they can look in the YouTube chat and then tweet to us really fast and you can win those tickets. By the way, the foundation is going to have more of these events. This is going to be an event that happens every season. So you can join the foundation and you can just buy the tickets next time or for a lot of the other events too. So keep that in mind. There are our nonprofit partner. And I do want to thank some of the folks that have been making donations already tonight. So it's just been awesome. Now, Patrick, time to find out what's up in the sky and what can we see this month?
All right, so yeah, let's go to our March sky report, and something that will affect on when you're going to view the night sky, or when you're going to observe the night sky, is a time change that occurs on March 13th. We have to turn our clocks forward for all the states in the United States that have the daylight saving time rule in effect. So that's March 13th, so don't forget to do that. And as a consequence of that, that means the sun sets an hour later than the previous day. So that means that you get more sunlight or more evening light in the evening and less in the morning. So what can we see in our evening sky then after the sun has set? Well, as we look into the evening sky, we notice that there are no planets. All the planets have migrated west of the sun into the morning sky. So what we have left are the stars of winter, which are now predominant in the southwest as you look towards the south. And these stars comprise of the brightest stars of winter. So there's a chance to look at the constellations of the winter sky. And the three of them, which are highlighted here, Taurus, Orion, and Canis Major, are now setting round about midnight. So they're kind of diving towards the western horizon earlier now. As Katie showed, I took this picture just before midnight last month, showing these three constellations all lined up just over the mountains there to the west, a very beautiful sight. So now we have the winter constellations moving to the southwest. What about the constellations of the spring? Well, they're located in the southeast. One of them is the largest constellation in the entire night sky. There's 88 of them altogether. This constellation is called Hydra. It spans over 100 degrees.
Hail Hydra.
Yes. It spans 100 degrees from the north to the south. The head is marked by, you can see it like a little circlet of stars. Its brightest star is called Alphard. And because it's made mostly of faint stars, you really need a kind of dark sky or a suburban sky to see this constellation rising in the southeast. Now, something that you might be able to see more easily from bright city lights, especially from Los Angeles, is Leo the Lion. On March 15th, the moon is in Leo the Lion. The head, if you join the stars together, the head and the mane of the lion forms a backwards question mark. And then the hindquarters is just a triangle of stars, and you just connect them together. You have the entire constellation of Leo the Lion. Another constellation, which is also a part of the zodiac, along with Leo, is Virgo the Maiden. And connecting those stars together, you find that it makes a letter Y in the sky with its brightest star called Spica. The rest of the stars shown here, connected, are just very faint, and so you need a moderately dark sky sight to see them. So the visibility of the constellations in the southeast in the evening sky heralds the arrival of spring, and that begins on March 20th with the vernal equinox, and the time of exact time of spring is, first day of spring is 8:33 a.m. Pacific Daylight Time. So this is when the sun is located exactly on the intersection of the celestial equator, the Earth's equator projected into the sky, the sun's path, or the ecliptic, and the 0 hour of right ascension of longitude in the sky. So from Los Angeles at local noon, the sun stands 56 degrees above due south at that time. Also, it is the first day of northern spring in the northern hemisphere and the first day of autumn in the southern hemisphere. And as you can see, the Earth there with the polar axis kind of lined up along the terminator of the Earth, which represents the dividing line of day and night. We roughly have an equal day and equal hours of night. As we look towards the morning, if you were to stay up all night and watch Virgo, you notice that it will move over to the southwest around about 5 a.m., roughly in the middle of the month. And if just above the bright star Spica in Virgo is the bright orange star Arcturus, and it's in the constellation of Boötes. And then we have to the southeast some of the summer constellations, starting with Scorpius the Scorpion. Its bright red star is called Antares, Chris's favorite star. And the constellation next to that, which is also a constellation of the zodiac, is Sagittarius. And if you draw the bright stars together, you notice it forms the shape of a teapot. Now, the extra bonus for the morning sky is over in the southeast, a little bit further to the east. And there are two planets there just rising. The brightest planet is Venus. And right next to it is the planet Mars. We'll zoom in a little bit and we'll see that not only do we see Mars and Venus, we also see the planet Saturn. So there's 3 planets up there early morning. Now, towards the end of the month, we have a beautiful sight. So we see the 26-day-old waning crescent moon is below the trio of planets, Saturn, Venus, and Mars. And Saturn and Venus actually are about 2 degrees apart, so it's a beautiful sight not to be missed. Our moon phases this month on 2nd. It is the new moon is the 2nd, and 10th is the first quarter. Full moon is the 18th, and the 24th is the last quarter moon. And then we have another new moon because the month is long, and that's on the 31st. So that's our sky report for this month. So go out and enjoy the night sky.
So Patrick, that's a fantastic sky report, a lot to see, but I have a question. We call a second full moon a blue moon. Is there a name for a second new moon?
Yeah, some people refer it as the dark moon or the black moon. It's it's not as notable as the blue moon, but
hey, because you
it
can't
is-
really see it,
Yeah,
and that's
you
what
don't
it's known for.
well,
So there's nothing to
shouldn't-
see for a second time.
well, there's nothing to see, and you shouldn't be looking for it anyway because it's too close to the sun, and so
That's
we
right.
all know that we shouldn't be looking near the vicinity of this anyway.
Yeah, you don't want to do that, but it can be great fun to see when you can first see that first crescent. And I know that a lot of folks will go to great lengths to do that. They'll put a telescope up against a building, so they're blocking out the sun, and they try and catch it during the day. But you have to be super careful and be professional. And don't ever point a telescope or binoculars at the sun unless you're professional and you have the right filtering. Don't even look at the sun with your eyes unless you have the right protective gear. So just be very careful about that, folks. It's no joke. You really can lose your sight, damage it forever. So, but anyway, there are lots of stuff to see in the night sky that won't damage your eyes. And I can't wait to see that morning grouping of planets and the moon. It's going to be really spectacular. So going to be a good reason to set an alarm to get up just a little bit earlier than my dog normally wakes me up. So now we've got time to move on to out to launch with you, Chris. I know that some stuff has been launching and there are plans for more. So what do we have in store for us?
Yeah, absolutely. Let's have a little look at what's going on with the world of launching and so forth. Of course, we're talking about things that happen or leave the Earth, that are off the Earth, but of course, all those events are also connected with things here on the Earth. So I will at least want to mention here something about the larger situation going on, because the international situation involves 2 of the leading spacefaring nations. The United States and Russia are having some difficulties at the moment, a period of strained relations. You may wonder what this means for space exploration. Well, here's a quote from NASA, and this is Kathy Luter. She's the head of NASA's Human Spaceflight Directorate. And essentially her quote there is that the teams are continuing to work together. The people are actually working together day-to-day basis, operating the space station. There's no problem with them. They are cooperating as they usually do. They're consummate professionals, and we do not have any information to suggest that anybody is going to be making any immediate changes to how the US and the Russians cooperate on the International Space Station. Of course, that's our immediate ongoing thing that we have. There are longer term questions that, if people aren't getting along too well, we might have to address. One of the things that folks may know is that United States astronauts have flown to the space station with the Russians in their Soyuz spacecraft. In the past, when the space shuttle was operating, Russian cosmonauts would fly as crew members on the American spacecraft. And now they can do that again because of the Dragon spacecraft from SpaceX. Now that it's operational, the policy of exchanging seats would allow Russians to come in and fly on Dragon. Now, what is just the only immediate question I think that really is before us with regard to this is that an American was supposed to be coming home with 2 Russian cosmonauts and landing in Russia at the end of this month. Mark Vande Hei, our astronaut, was going to go home with them. Well, that was the plan. No one has suggested a change. There may be no change at all. But that's the most immediate thing I can think of. They did have a plan in the end, right, in September, where a cosmonaut was going to fly on Dragon and an American astronaut was going to fly up with 2 cosmonauts. Is that plan still going to happen? Well, as far as I know, there's no change yet. Watch the headlines, but the main thing is, for right now, there's no immediate change. Longer term questions, sure, we do have some. The Russians build a number of rocket engines that are used, for example, in the Antares launch vehicle, American vehicle. The Atlas rocket uses some Russian-derived equipment as well. Will those supplies of parts be interrupted? Will we have to switch to a different rocket engine? Who knows? Now, more seriously for our Mars fans, though, the ExoMars lander, a partnership between the European Space Agency and Russia, was going to have the Russians doing a lot of engineering to build the ExoMars lander. So that, too, is a question. Down the road a bit, we'll get it all sorted out.
Hey, Chris,
things are all right.
Chris, before you continue, we're having a little problem with your audio sort of cycling, getting louder and quieter, and I'm not quite sure why.
Well, I will try to be monotonal. How am I?
No, it's not your speaking, it's your microphone.
Oh, okay. Well, can't change mics in the middle. Or actually, maybe. I have had a suggestion.
Yeah, it's a night of audio issues tonight, folks.
This
has been quite a while since we've had any tech issues, but tonight's the night, evidently. So I'm glad they're all clumping together into one episode.
Fair enough. How do I sound now? Did that fix things?
It's a little better. We can hear you. It'll work out okay. I'm not sure why it is that way.
Well, let me leap on through, and hopefully you'll be able to hear me okay. We did have a problem with the launch of a small vehicle, the Astra launcher. Its first launch from Cape Canaveral. It was their 7th launch. Unfortunately, 6 of them had failed. They were launching up from Alaska, and they had one successful launch into orbit from Alaska, which was their 6th launch attempt, was successful. But number 7, unfortunately, their first launch from the Kennedy Space Center in Florida, and the second stage did not detach properly from the first stage, so it's a failure. But you got to remember, you try again. I'm sure these guys will be back. They'll get it figured out. It's a new vehicle. The Russians are sending up 3 cosmonauts on the 18th. Interestingly, by the way, these are all 3 Russian cosmonauts. The original plan several months ago was to have an American launching with them on the 18th. But NASA decided to wait till September. So this flight is going to be all Russian cosmonauts. We have a private space mission coming up with the SpaceX Dragon. The Axiom 1 mission has essentially paying passengers, with the exception of one of them is a former NASA astronaut, second from left in the picture. The others are essentially just paying customers. They're going to spend 8 days on the International Space Station. The Axiom Space Company that's arranging the mission is looking to develop a space station, a new space station in Earth orbit that would serve both tourists and scientific research. For a regular crew rotation for the United States, in April, we have the Crew 4 mission. These are all, 3 NASA astronauts on the left and 1 European astronaut on the right. They'll be going up for a 180-day stay on the space station. Looking at the Starship, or the Starlink business that was already mentioned, why did that happen? Why did we lose some satellites? Isn't the sun always a factor? Well, SpaceX has a policy of launching these satellites into very low orbits to start with. They always operate at a fairly low orbit. That's what they do. But SpaceX will launch them only 130 miles above the Earth's atmosphere when they very first start, because sometimes satellites won't work, And if SpaceX commands the satellites not to raise their orbit, they have small thrusters on them. Just leave it alone. The satellites will re-enter very quickly over a few days and will be disposed of. So that was a policy they had intentionally to do that. Now, if the Earth's atmosphere is energized by a geomagnetic storm, though, it increases the density of the atmosphere. And that's what happened here. They launched a batch. They were all still at their preliminary low orbit, hadn't raised it yet, and got caught by that. Now, the SpaceX has launched a bunch of replacement satellites already. So this is no big deal. And by the way, they did launch them to a slightly higher orbit this time. Starship, you may be wondering what's going on with the big giant rocket in South Texas that SpaceX is building. Still waiting for approval from the FAA. Well, not entirely waiting, because it may be a delay. We don't know when it'll be approved. Kind of strange that they didn't get it formally approved in advance, but the plan now, SpaceX is launching ahead with building a launch pad and tower at Kennedy Space Center in Florida, where they certainly have permission to launch. If they have to wait to launch from Florida, it might be a delay towards the end of the year, around about that time. We do have a return of Jared Isaacman. You may remember him from the Inspiration 4 mission, a private mission to do fundraising for St. Jude's Research Hospital, an Earth orbit mission. Well, turns out Jared Isaacman likes being an astronaut and has actually purchased yet another space flight. In fact, 3 more are planned. The one coming up that you see here is going to launch toward the end of the year with a couple of other, the other 3 people there to the right are SpaceX employees. And if you see the picture of the Dragon in space, you'll see he's doing someone's going to do a spacewalk. And that's because SpaceX is designing a brand new spacesuit. So that's going to be an exciting mission. We don't know too much about the next Dragon mission that he's going to be on, but we do know about the 3rd one he's going to be on. The 3rd one is he intends to command the first human flight of the giant Starship rocket in Earth orbit. Wow. Now that won't be this year. We'll have to wait and see just when that happens. So that's something we're waiting for. Here's something else we're waiting for. What about the big giant moon rocket, Artemis 1 mission with the Space Launch System? NASA's latest words, we're probably going to have to wait till May at the very earliest. Maybe it's going to be June. We'll find out more about that as announcements are made. Well, anyway, that's it for the world of launching. Hand it back to you, Dr. Retzel.
Thanks so much for that, Chris. And do try and maybe reset your audio. You were in kind of an RR Lyrae like cyclic, louder and quieter and louder and quieter. So we apologize for that, folks. But you know, these sorts of things do happen. All right, Patrick, time for us to talk about Juno and Jupiter and what's been going on there.
Okay, yes. So so Juno, which is NASA's mission to study the planet Jupiter, has performed its 40th close pass around the giant planet, and that closest point to the planet is known as Perigove, and this is the Perigove number 40, which is indicated where that blue arrow is. At that point, the spacecraft is roughly about 2,000 miles above the cloud tops of Jupiter. Now, normally, when we look at Jupiter through a telescope, we see a banded planet just looking exactly like this. But Juno has a unique view. It actually flies directly over the pole of Jupiter. And this is the graphic that shows that, and gives us a view of Jupiter's poles, north and south, that we can never see before. This image was taken from the last Perigove in January, number 39, and it shows what it looks like when Juno approaches Jupiter. This is a view that you cannot see from Earth, and basically shows you a crescent view of Jupiter with a unique view. Of course, the unique view is the polar region, and here we're looking down at roughly about 16,000 miles from above the North Pole of Jupiter, and you can see it's covered. It's very different. It's not banded. It's covered with lots of various circular storms or cyclones. One of the interesting things about Jupiter is that the polar region is that the cyclones near the North Pole of Jupiter, there's 8 of them that basically cycle around the North Pole. They're all labeled here. And to the south, around the South Pole, there are 5 storms that circle around the South Pole. The plus there was a 6th storm that tried to barge into the other 5, but later did not make it. So there are currently 5 storms positioned roughly in a pentagon, roughly about 72 degrees apart, that are in a very stable configuration that go around the South Pole. This is just a composite image taken from several parajoes to see these interesting cyclones that go around the poles that are very intriguing for the investigators and scientists. Taking a look at some of the other pictures taken on Parajo 40, here we see in high latitude image of a folded filamentary region, and you can see it's kind of still bluish in color. And we have to remember that these images are color enhanced, and so color exaggerated so we can see some of the features, and also the contrast is boosted. We can see how beautiful these are. The whitish clouds are Mauna ice crystals, which are from pop-up thunderstorms. A little bit further down, and this image is taken roughly about 2,000 miles, so near the closest point, it's Parajo. Here we see a storm, circular storm, which looks like the Great Red Spot, but isn't. There are many tiny storms. This one's probably roughly about the size of Texas, kind of swirling around in the middle latitudes of Jupiter. And talk about just close to the equator, here is a turbulent feature, which actually is basically caused by a jet stream just below the more stable equatorial belt of Jupiter, and beautifully color enhanced. And you can see all the very finessed and fine details of the upper level clouds, and some of the deeper levels, which are kind of in dark, kind of darkish gray color. A unique picture that we've not seen for a while. And this is Jupiter's taken just looking at the southern hemisphere, looking at a latitude of 55 degrees south. That dark elongated feature right at the top there is the shadow cast by Jupiter's largest moon, Ganymede, just near the terminator of Jupiter. So Jupiter frequently gets these shadows, or across from moons. And if you were in that area, you would see a total eclipse of the sun by one of Jupiter's moons. Talking about moons, Juno is still proceeding to get closer and closer to the icy moon Europa, which is the 6th largest moon in the solar system. At left, that was a picture taken when Juno was just about 51,000 miles away. This time, just last month on PJ 40, it took a picture at 29,000 miles, and you can see the difference. You can see a lot more detail. This is also a unique view. We're looking down at the North Pole of Europa, an area that we've never seen before. Now, this is not the closest it's going to come. In late September of this year, Juno will swoop just about 221 miles above Europa's surface, giving us the closest flyby of any spacecraft since 1997, when Galileo flew a little bit closer, 124 miles just above the surface of Europa. All of this information will give us some data for upcoming missions, such as the Europa Clipper, which is destined to arrive around about 2030.
Yeah, the Europa Clipper mission is really going to be something. Patrick, we had a question in our chat. Folks wanted to know, how long are those polar cyclones? How long do they last? Do we know? They seem to have been there quite a long time, but do they compare with, could they last as long as the Great Red Spot has lasted?
Yes, well, those polar cyclones have been remarkably stable. In fact, I know that you're going to cover some of them. There is two images that are in your story. Basically, that they can last for a number of years, and they're in a very stable configuration, which is intriguing for the scientists. They think it can last maybe up to 100 years or so in that configuration.
Wow.
But yeah, it's extremely stable, and they want to find out what the mechanism of why they are so stable.
Yeah, very, very cool stuff. Well, thank you for answering that. I figured you'd have a better finger on the pulse of those storms than I do. Well, now it's time for our final story of tonight, and we're going to talk about Saturn, believe it or not. Some interesting things been happening at this beautiful jewel of our solar system, my favorite planet besides Earth. Earth is my favorite. It's where I keep all my stuff. But Saturn's pretty great. These rings are gorgeous. And believe it or not, we didn't know how fast Saturn rotated. What's the actual spin rate of it? Sure, we could watch the clouds whiz around, but are they going faster than whatever's spinning inside? And when we went by the first time, when we flew by, we measured a period of about 10.5 hours. Well, we went back with Cassini, and suddenly we measured a period that was different. It was like 10.2 hours. And it changes, or I forget. I might have that backwards. Maybe it was 10.2, and then Cassini found it by a different time. And we thought, my gosh, could the entire ball of Saturn be changing? How would it's massive? It's huge. There's no way it could change the rate it's spinning. So they needed to figure out what was happening. Well, the Keck telescopes were just recently used to measure a speed of some aurorae. They figured that they were measuring the spin rate before by noticing when a repeating radio burst would come by. And they thought that was caused by the inside of the planet. Well, then they learned a little bit more about it and said, these radio bursts might be coming from the aurorae. That's right, that blue glow up at the top of Saturn. They thought maybe there's something in there that's causing that radio burst. And if you change the rate the aurora is spinning around, you might change the rate of those radio bursts. And they thought that might be what's happening. So indeed, they used the Keck telescope to measure the speeds of the winds up in the ionosphere, the very upper region of Saturn. And the prediction was that in order to make this happen, you'd need to have two cyclones. You can see there's two centers of spin up there working together to funnel that material through the center, accelerate it quickly, and actually activate the aurora being created by these high-speed winds. So it's another mechanism to make some aurorae. Now, the aurorae are happening in the infrared part of the spectrum, but notice that arrow is changing directions. Sometimes the wind's coming at us, as it's about to now, and sometimes the wind's going across, and sometimes it's going away from us. And that actually, if this was correct, was how the spin rate of Saturn was being not really influenced, but we were being tricked into thinking the speed was going at different rates based upon this. And indeed, they were able to see that, and they detected evidence for these two cyclones up at the top of Saturn. So a really remarkable finding that they used with the Keck telescope. Now, you might think, is this related to the hexagon? You've heard about the hexagon on Saturn. Indeed, you can see those clouds down there. Actually, no. Those are created by storms that are stable in the lower part of the atmosphere. And in fact, the storms look a lot like those storms at Jupiter. This is the picture of Jupiter here that Patrick was talking about. And you can see that stable configuration of 5 storms with one in the middle between February 2017 all the way to October 2021. And they're still there doing their thing. So those storms have nothing to do with these ones that are higher up that are causing these aurorae. The ones that are higher up are up above that haze layer you can see there. They're up in the ionosphere, well above the clouds we're seeing. So the two phenomena are not directly related at all, other than the fact that they are sort of circulations in winds that create them both. But the ones that they measured with this, the aurorae on Saturn, were a little different. And here's another picture, a beautiful picture of the Saturn aurorae that you can see down at the bottom of Saturn here in this really cool infrared glowing image. So that is our last story tonight, folks. And we are a little bit ahead of schedule, which is just terrific. And at 9 o'clock, we are going to turn and join Shadow the Scientist. So I'll put up that No, he's not online yet, but I'm going to put up the graphic here for the Shadow of the Scientists. And we are going to join Raju, who was our guest speaker tonight, Professor GuhaThakurta from Santa Cruz, department chair right now, as he says, nobody really wants to do that work because it's a lot of work and everybody's telling you what they think should happen and how they expect you to run the department. And you have to make all those decisions, which oftentimes doesn't make a lot of friends. So it's a very, very difficult thing. That's why he was talking about that. But I want to turn to our YouTube chat right now. And this is a hint to all you folks out there that are watching that don't have a YouTube the channel or a membership that you can join to, although it's free, you don't have to pay for it. But if you have a YouTube login, you can log in and chat to us. So are there any questions out there that you'd like to have answered? I'm going to take a look here and scroll up and see what people are saying. There was a question, something about an eclipse is more specific, R star. I don't know what was going on there with Alan, unless, what did Bill say? Oh, I don't know. They're talking about eclipses and Ganymede and covering the sun, and I don't know. They're going on about something, but I'm not seeing any questions there directly related. So I'm just going to tell you a little bit about what Raja is going to be doing with the Keck telescope in case you joined us a little late. So in about 5 minutes, we're going to join his Zoom stream, and we're going to stream it right here on YouTube to you. And he's going to be operating the Keck II telescope and the ESI spectrograph. It's an Eschell spectrograph, takes very high resolution spectra, and he's going to be getting them of stars that are very far from the center of our galaxy, things that are twice as far as we are from the center of our galaxy, but out in the halo, so pointed up away from the disk. Those stars are pulsating, so he can know exactly what distance they're at because they all have about the same brightness. So all you have to do is measure how bright it looks in the sky, compare it to how bright you know it really is, and that tells you how far away it is. It's kind of like if you have a candle that burned exactly the same brightness. We call them standard
candles.
Yeah, standard candle. And if you put that at some distance and you'd say, gee, that thing is 4 times fainter than the one that's 1 foot away from me, well, you'd know it'd have to be 2 feet away from you because it drops with the square of the distance. So if you scatter candles out on a field at a whole bunch of different distances, if they all burn equally bright, you could sit and point to the ones and rank them in brightness, and you could figure out exactly how far away they are. That's what he's doing with these RR Lyrae stars. And then he's going to measure their spectra, which tells you information about their chemical composition. He'll be able to measure their speeds and track down whether they came from a dwarf galaxy that has been cannibalized, that's being ripped apart by the gravity of the Milky Way, and find out, are they all traveling together? Can they find out, are there groups of these? So it's a way to sort of do galactic archaeology in a way, go back and pin down the history of the formation of our own galaxy. These objects came from somewhere. They came from these dark matter clumps you're seeing in this picture, or that you aren't seeing it right now on our YouTube stream, but in the emblem, the dark matter clumps kind of all bridge between galaxies. So tonight, we're going to have the chance to join Raja on his Zoom stream with his Shadow of the Scientist program. So hang on with that, folks, and we'll turn to that as soon as he's gone live. But right now, we're going to run our credits, and we'd like to thank you all for joining us tonight at All Space Considered, and we'll be back, believe it or not, on April 1. Now, whether the bosses let me do an entire show that's just all jokes and it's all fake, I kind of doubt it, but we might sneak one in. Maybe we'll have one story that you're going to have to figure out which one is the fake one. So we'll have to wait for that. So before we finish here with our credits, once again, I'd like to thank Chris Butler again. Thank you so much for your out to launch story and all your contributions. Patrick, so as always, wonderful Sky Report, awesome Juno Report, and it's just a pleasure to do these with you. Katie Flynn, I know you're out there somewhere. Wonderful, beautiful astronomical images, pretty pictures, and the space weather keeps getting more and more interesting as this sun is getting more active. And of course, we thank our guest Raja, who will be joining. We'll be joining him in just a couple of minutes. And as always, Griffith Observatory is owned and operated by the City of Los Angeles under the Department of Recreation and Parks. And we always would like to thank Griffith Observatory Foundation, our nonprofit partner that makes so much of what we do possible. If you'd like to join the foundation, you can find that link on our webpage, also in the YouTube chat. It's been pasted. So thank you so much. We're going to run our credits, and then we'll turn to the Shadow of the Scientist stream in just a moment. Thank you all.
Good night.
Well, folks, we have joined Shadow the Scientist with Raja, and it looks like they are getting ready on their observing run. So Raja, the VNC is a virtual connection. He's connecting to the telescope in Hawaii with it's like a remote desktop called VNC. I hear you, Raja. I don't know if I'm unmuted, but yes.
I can hear you.
Yeah, that was us, Raja. We can hear you just fine.
And I can see that by looking at this image, or if you can see my cursor, you can see multiple images of a star, 36 images of a star as they focus the telescope. So I'm going to see if we can see it on one of our other windows. Don't see it there. Let's see, normal, center. Right, we can, this faint image, it looks faint because the sky is still bright after sunset. I can see that by looking at this image. If you can see my cursor, you can see multiple images of a star, 36 images of the star. I'll be right back. So I'm going to see if we can see it on one of our other windows.
Exposure complete. DCD readout complete.
So, folks on YouTube, what you're hearing there is indeed the notification that the CCD or the chip collects the data read out.
Delay is the problem.
And Raja, if you can still hear us, you should mute your YouTube stream.
Folks, I assume you can still hear me okay on Zoom?
Yes.
That's great. Thank you.
Yes.
So I actually have two different Zoom calls running, one with the Keck folks and our science team, and one with all of you. But I'm just going to check in with you think. So I'm going to turn my sound off here for a moment.
Good. Perfect. We've been muted to Raja, so we can talk to our YouTube channel, and he won't be interrupted by
I just checked in with the folks at Keck, and what they're doing is they're in the process
Exposure
of
complete.
focusing the telescope. And if you look closely in the upper right part of the screen that I'm pointing my cursor to, you'll see two images of a star. They look like a hexagonal pattern of Keck segments, because that's exactly like David Reitzel was saying on the Griffith All Space Considered show. This is how they focus
DCD readout
the James Webb
complete.
telescope. You're seeing the individual images from the different segments of the Keck telescope. 36 segments, so you see 36 images of the same star. And here are 36 images of a fainter companion star, or companion in the sense of being close to it on the sky. Now that they've focused it up, you see single images, not 36 images, now that they've sharpened up the focus of the telescope. So this is a particular focusing technique called MIRA, M-I-R-A, stands for mirror alignment. And they're talking about aligning the segments, the 36 segments of the 10-meter mirror. And just so, yeah, the panic button. Ben has asked. So the panic button is if something goes horribly wrong with the exposure, and you happen to point towards something very bright, you want to stop it right away. That's what you'd use. I just want to say that just to give you what to expect, it's 9:07 in California, depending on what time zone you're in. But 9:07, 7 minutes past 9 p.m. and 8 minutes now past 9 p.m. So what we're going to do until about 9:45, so for another half hour, little more than a half hour, is we'll be taking spectra of a few bright stars before we settle on a faint star, a distant RR Lyrae, on which we will spend almost 2 hours. So for the first 45 minutes, we'll be hopping around from one star to another. There'll be a lot going on. The next 45 minutes, that is from about 9:45 to 10:30 California time, we'll be sitting steady on one faint star. And during that time, I'll be able to spend a lot of time explaining what you're seeing on these screens about our science experiment, answering questions. So you'll see more activity early on, less activity later, but more explanation later. Okay, thanks.
So folks, what you are seeing is the control panel there for the instrument. This is how the astronomers control the various instruments and various targets. You can see target lists. It's all there for the astronomer to control. Right now, he's on another Zoom call with the folks that are up at Keck itself, and he's talking to them, making sure that everything is going properly. So keep in mind, this is an actual data run. He needs to get good data for himself and his student, and he'll talk to us when he's able to do so. We are literally eavesdropping on this run. I'm not sure what that dark box in the middle is. I think that's something with Zoom that it's not being shared quite correctly. but you are seeing literally the control panel for the telescope. Well, the instrument on the back end of the telescope. They don't let the astronomers drive the telescope. We have specialists that do that for us.
So folks on Zoom, you see this little star with a box on it. This is a bright RR Lyrae in the Milky Way, not too far away. And we're going to get a spectrum of this star soon by adjusting the pointing of the telescope so that the light of the star goes through one of these slits here, these vertical dark lines that you see here that my cursor should be showing, the vertical cuts in this piece of metal. There you can see my cursor now. A little bit of a lag, sorry. These vertical cuts are cuts in a piece of metal. The metal is reflecting light off the sky, but where it's not reflecting because there's a cut in this piece of shiny metal, the light of the star is going into the spectrograph, and so we can take a spectrum. So we're getting ready to take a spectrum of the star whose ID and coordinates are highlighted in the box immediately below. This is the row that's highlighted in yellow. Index 11, name is PS1M. PS1 is the name of the survey from which the RR Lyrae was, in which it was discovered, Pan-STARRS 1. M because we're monitoring it. 9139 is its ID in that survey. And then you have what are like the longitude and latitude, the RA and DEC of the star. And then you have the coordinate, the equinox of coordinates, 2000.0, because the Earth's axis is precessing over time. The Earth's axis of spin is wobbling. We have to specify a year for these coordinates. We have to find. We always use a reference here for this, and we use 2000.0. So we're getting ready to take a spectrum of this bright star. When a spectrum starts, when we start taking a spectrum, what we'll do is we'll change these. We'll change these parameters here on the instrument. So I'm going to get ready to do that.
So folks, they did get rid of that box, which was good. And now we can see those controls for the instrument itself, what mode it's running in, what the bias is. That's how much, essentially how much you're biasing. Well, that's the observation type. A bias image tells you the characteristics of the chip itself so that we can calibrate the how bright things are and calibrate our images that we get. You have to take a bias image. You need a lot of them. You need dark images as well, and also things called flat fields. So most of these things are taken fairly early in the night, but if you want really, really high caliber, high quality data, you want to take them in the same conditions that you're getting your observations. So I'm sure they took biases right before they began all of this tonight. Notice he changed that name to object. And the time of it was just a 1 second exposure, so not very long. I'm thinking he might change that. We'll see. See, now he's saying take 2 exposures and make them 1 second long. There he goes, 120 seconds, so 2 minutes. So he's updated the CCD information.
So folks on Zoom, you saw how stars were streaking across this field of view because the telescope was moving, so the stars looked like they were shooting across the sky, like they are now. And what we're doing is we're taking that star, that's a bright RR Lyrae, and we're putting it on the slit. You can see some of its light is spilling over, but most of it is going into the slit, and we're going to get its spectrum. And we're going to take a 2-minute spectrum. You can see 120 seconds set up here, and we're going to take 2 of those exposures. And as soon as I hit the yellow expose button, it'll be able to start. So I'm just waiting for them to give me the go-ahead to start the exposure.
For a while, the focus was different on the bottom and top parts of the guider, but it looks like focus now. Like, I think visually it looks like focus.
So the sky on Mauna Kea is just about now getting dark enough. The sun is about 12 degrees below the horizon after sunset. Between the sun being 12 and 18 degrees below the horizon, the sky continues to get darker. And that takes about half an hour to go from 12 to 18 degrees below the horizon. During that time, we'll be observing some bright stars. Then we'll go to the distant RR Lyrae. Bright RR Lyrae first, and then distant faint RR Lyrae next. Rita and Arena, please give me a go-ahead when you want me to start the exposure. No problem. Thank you. Thanks, Yuting. We're going to do two-minute exposures. I'm going to hit the expose button. I have object, 120 seconds. I have focus and echelette mode. I have 1 arc-second slit, Deca, clear. Okay. Everything look good to you? Michael?
Good to me. He wasn't asking me, but I'll answer anything.
Yes? Thank you. Okay, I'm going to start. So for the folks on Zoom, I hit the expose button, you saw. And now this box turned gray, and it's going to count up from 0 to 120. And there's a green box here that's going to count down from 120 to 0. So there's a countdown clock and a count up clock. It's a little delayed on the YouTube link, a little bit delayed if you're watching this on YouTube, but on Zoom, you can see this happening. It's about 20 seconds into the exposure now.
But Raja is also delayed on YouTube. So if you're on his Zoom
we'll
call,
soon see a spectrum of this bright star that's sitting on the slit here. It has the completely romantic name of PS1M_9139. As I explained, it's from the Pan-STARRS 1 survey. They discovered this RR Lyrae. This is not particularly far away, but we want to use it to monitor the spectrum. And the reason we do this, as these stars pulsate, literally the physical front surface of the star is moving towards us or away from us. And because of that, we can see a shift in the velocity of the surface of the star in real time. And that's what we're doing with the bright RR Lyrae in this part of the program. I'm going to switch screens so you can see when you see the 36 images of the star now. That was from the time we were focusing the telescope. And as soon as this readout over here, as soon as this 86, 87, as soon as it hits 120 and this hits 0, the countdown hits 0 and the count up hits 120, it'll start reading the exposure and we'll see the spectrum of the star. So I'm going to stay on this screen until this countdown finishes. And as soon as the countdown finishes, I'll move to the other screen so you can see the spectrum of this bright star as it reads out. This will be our first spectrum of the night.
Exposure complete.
Okay, I'm going to switch screens. And in this screen right here, we should see the spectrum of the star up here. And what I'll do is I'll do histogram equalization. So we should be able to, there you can see the spectrum of the star. It's reading out, that's why it's scrolling down gradually. It's actually reading out the CCD detector. And the spectrum is in the form of these curved lines. For YouTube, it hasn't appeared yet, but it will appear soon.
CCD readout complete.
And so now, CCD readout complete, meaning it should have started the second exposure. So if you go back here, if I go back to this control box, this box has turned gray again. And now instead of 2 exposures, it says 1 exposure remaining. You think I'm going to highlight the next target now? Is that row 12. You think I'm going to highlight row 12 as the next target? So as soon as this one finishes, we'll go there. We could shorten this one if you want. Should I shorten it to 1 minute or 90 seconds? How about I make it 80? So we're changing the exposure time because the star is bright enough. And so, so Rita and Irina, we've highlighted the next target. As soon as this readout finishes, which is in about 10 seconds, or as soon as the readout starts, we can go to the next object.
Exposure complete.
Okay, so we're going to see another spectrum of the same star. And can you see how the star got fainter? Can you see that as it's reading out? Because we cut the exposure time from 120 seconds to 80 seconds. So we should be getting, 2/3 as much light. If you look closely, you'll see a gap in the spectrum right there. I've highlighted the next target already. Yes.
Okay, you guys are ready?
Ready to move. I'm going to zoom in a little bit. So let's see if I can do that.
DCD readout complete.
The information content of these spectra is spectacular. I want to point out something here. Let's see if I can find it again. Let me normal center. Let me click on this. So it should be centered.
Star.
This is a single star. It's a single star whose spectrum we're seeing. A spectrum of a single star. In fact, let me just zoom in a little bit more. So this.
About 22 degrees elevation. That's okay with you guys, right?
Yeah, it should be fine. The elevation should be fine. The way you read these spectra is it's like reading reading lines of sentences in a textbook. You read across, then you read across, then you step down one, you read across the second row. Here, you read down, then you step one to the right, you read down again, you step one more to the right. There are 10 such orders. If I zoom out, you'll see there are 10 such orders going from left to right. So you first read down, this is increasing wavelength. Then you step across and you read down again, the next order, and so on. But I was zoomed in on this part of the spectrum. I'm going to zoom in again. So you can see quantum mechanics in action in the surface of this RR Lyrae star, this bright RR Lyrae star, bright by Keck standards. And what you're seeing here, this dip in light is because as the light from the star is trying to come out, hydrogen atoms are intercepting this light, and electrons in those hydrogen atoms are boosted from level 2 to level 3. So you get H alpha absorption. These two dips over here, that one order to the left, these are shorter wavelengths. These are produced by atoms of sodium in the atmosphere of the star going through a similar process where electrons are being boosted up by photons, and those photons are therefore being absorbed and not being allowed to get out of the star. Not all of the photons are getting out. That's why you see what these are called absorption lines. This is from neutral sodium atoms, and this one is from hydrogen. There are actually many such absorption lines on the spectra. But before we do that, I want to go back to our other screen and make sure that we are getting ready to get the next star onto the slit. You'll notice that the background has gotten much darker because the sky is getting darker. You think I'm going to type in the coordinates of the... Let's see, I want to type in the coordinates. It's 13942.
Now, as he does that, folks, I want to explain something. In those spectra you were seeing, there were also lines going across the spectrum. Those were night sky lines. Those were emission lines of our own sky. Our sky glows at certain colors, and it creates those lines that cross the spectrum. So the stars, the narrow bands that go vertical, and our own sky causes those horizontal lines, and that's our glowing atmosphere.
You think it looks like the exposure started for the second star. What would you like the exposure time to be? It looks like the 80-second exposure has started for this object. What would we like the exposure time to be?
Yeah, I think just keep the same. All these three monitor stars are, you can see initially the same.
Okay, so 80 seconds is okay? Exposure time of 80 seconds?
I think anything on like 60 seconds or 80 seconds.
Okay, I've got it at 80. I won't change it. But up the exposure, number of exposures to 2, I've changed the ID here. So hopefully we should see a nice spectrum in a few seconds, in 23 seconds, 20 seconds. I'm going to switch screens so we can see the new star spectrum readout. I'm just going to zoom in a little bit.
So folks, there you can see those horizontal lines
So
I
the
was
exposure is
talking
complete.
about.
Now it should be reading out. And one of the main things you'll see change are these dots will change. These are cosmic ray hits on the detector that will change as it reads out the new star. So I'm waiting. Yeah, there we go. You can see that this star, the trace is a lot wider. You think I'm not sure why, but the trace of this star looks a lot wider than the previous one. It could be the low elevation, and we're getting worse image quality.
Yeah, I think it's some kind of blurry.
DCD readout complete.
This
I
is
mean,
what
we're
it's like
still
to
getting
observe.
plenty of signal, so I don't think that's a problem. I'm just going to zoom out. And I believe we can see H alpha still, which is just fine, which is right there. It's got broad H alpha. Yeah, you can see the H alpha is in a doublet, looks like a doublet because it's probably in shock mode. It's got H alpha emission and absorption at the same time. That happens during the shock. I bet that's what we're seeing for this star right now. I think we don't see sodium doublet in absorption, but we see the H alpha. The H alpha looks like a doublet right now. And I think it's probably we're catching this thing in a shock phase. Yeah, exactly. I mean, the other lines, this is H beta right here, I believe. Yeah, H alpha, that's H beta right there. You can see the calcium triplet. That's up in this order. Calcium triplet is over there. Let's see if I can zoom in. The calcium triplet tends to be weak in these stars. Let me just make sure that the second exposure has started. Yeah.
Exposure complete.
It's completed. Good. Okay. So let's highlight the next target. It's going to be row 14, right? Oh, you've highlighted it already. I see. Are we are ready to move there, right? You think?
Sorry, which one are we going to next?
So a highlighted target, row 13, index 13. Yeah, please. It's highlighted. And you think I see you've updated the object name. We should change this to 2 exposures.
DCD readout complete.
Is this another short exposure again?
It should be a short exposure, another set of 280 seconds. And this will be the last of our short exposure ones, right, Yuti? And then we'll go to a long exposure one. Thank you. Yeah, so this thing that you see crisscrossing across the screen for the folks on the Zoom call, this is because Rita and Arena they're on the summit of Mauna Kea, they're moving the telescope, and as they do that, the stars look like they're moving relative to the camera. The pixels of the So folks, if you're just joining the Zoom call, we're in the middle of observing some bright RR Lyrae. And in a few minutes, after we observe the third of these bright RR Lyrae, we'll go to a faint RR Lyrae and we'll take a very long exposure, series of long exposures. And at that time, we can introduce ourselves on the call and talk about what we're doing, explain what these different windows are that you're seeing here. There's, sort of 4 screens that one can share. Yuting and I are running this from home. Geronimo, do you also? We don't also do. Thank you. Yuting, I assume you're going to start. There you go. Okay, so we do have photometry of these stars, but we ourselves are not monitoring it right now.
Okay.
Yeah, the mag says 0.00 over here. We have the magnitude for these stars in a different spreadsheet. They're just not entered into this. But thank you for asking that. And I think you got. Am I right that you got connected to us through Alpha Sen?
Sorry?
Did you connect to Shadow the Scientist through Alpha Sen, the organization?
No, I found out through some colleagues, some astronomer colleagues from here, from Colombia.
Oh, from Colombia. Okay. Okay. I think they may have found out from Alpha Sen, which is an organization that's based in Central America.
Okay, probably, yes.
All right. So we are taking a spectrum of this star, this bright star now that's on the, whose light you can see is, some of it is going into the slit. It's a very bright star. Some of it is spilling out. And in about 20 seconds, less than 20 seconds, we should see its spectrum. Yuting, I hope the star's spatial trace is.
Exposure complete.
Hope it's not as blurry as this one. Oh yeah, it's narrower. You can see that. It's a bright star. This one is really bright. We are about 10 minutes away from 18-degree twilight, do you think? Or are we closer? I think we're closer, right? We're 6 minutes away. What was that again? You think what was that again? How many minutes are we away from 18-degree?
DCD readout complete.
8 minutes. Okay. Okay, so it started the second exposure, or starting the second exposure now. Second 80 minutes. This is a bright star. This is really bright. H alpha is booming right there. But it's interesting how you could see the metal lines in some, and sometimes you can't. So there are all these absorption lines here as well. This must be the Balmer series. H alpha, one of these must be H beta and H gamma, H delta. This absorption that you see here in this part of the spectrum is produced by the Earth's atmosphere, not by gases in the star, but in the Earth's atmosphere itself.
Yeah, those are a little harder to get rid of, folks. You have to look at a star that has
Let's see
very
how
few
this is
features in
doing.
it. A hot blue star will have very few features, and you can map out those absorption
we are,
lines from the sky.
On the second exposure here, Yuting, why don't you highlight the offset star for the science target next?
Though I have to say, folks, this does make me want to jump in there and help them observe. It's great fun to do this work.
Okay, we're ready to move there, Rita and Arena. Yuting has just highlighted the offset star for the first faint target.
Yes. So notice he's asking the telescope operator to move.
Right, Yuting, ready to go there, right? And do you want to update the object name then? Object ID?
Again, that's because they don't let the astronomers.
Is it just PS1 6487?
Experts to do that for us.
Is this your science target? Are you going to be here for a while?
DCD readout complete.
We won't be at this star for a while, Rita and Arena. This is an offset star. We'll do a blind offset to our faint science target, and there we'll be there for 2 hours.
Okay, so you probably want to set the parallax to something that's a bit farther over.
Yeah, about an hour west. Yeah.
Okay, sounds good.
I'm not yet looking at the schedule sheet. Let me bring that up. I'm going to stop sharing my screen while I do that. I've got your email, Yuting, and I'm going to bring it up. And then I'll share my screen again. Okay, folks, here's my screen share again. Yeah, Yuting, I'm looking at your screen share now. We are, it looks like you've crossed out one of the objects, 6431. Oh, you're right. Sorry. Okay, we're on 6487 now. So we've observed the first three objects, and now we're on the fourth one. Is this what we want, 6487? Oops, sorry. So folks on Zoom, these arcs you're seeing on this image here is because the instrument is rotating as well as the telescope is translating.
Might have been Katie, wasn't me.
So in just a few more minutes, what will happen is we will lock onto this very faint star that we are going to take not 2 times 2 minutes, but we're going to take 5 times 22 minutes. So it'll be a very long exposure, or the cumulative exposure will be almost 2 hours in length, 110 minutes. You think I'm going to put in the exposure time, if that's okay? 22 minutes is 1320 seconds, 1320. Do I have this right? Okay. We're doing 18 minutes, is it? Okay, 6 times 18, not 5 times 22. Okay, I'll switch that. So this number of exposure should be 6. And what is 18 multiplied by 6? 60, 1080? Yeah, 1008. Does that look okay to you?
It's good.
And we're not going to hit the expose button just yet because we're waiting for we're lining up on a very bright star that's close to this faint object. And then we'll do a blind offset between this bright star and the faint object. The seeing is good, so I think we should be able to see that faint star. These bright stars are super bright. Right. What is the difference between D off and P off? What does that mean? Oh, DES offset. DES offset, PS1 offset. Is there N off as well? I see it. Got it. Thank you. That makes a lot of sense. So I think when we do offset stars and we apply a blind offset, what was that, Rita?
So we think we're lined up with your offset target on the slit. So go ahead and offset, yeah?
Yeah, it should be. You should be able to offset. The offsets are listed, should be listed in the star list itself.
Yep. Looks like about minus 268 and like minus 0.8 or something.
Okay. Thank you. And the faint star that it'll put on the slit is not so faint. We should be able to see it. Unless it's going right into the slit now.
All right, we're guiding.
Is there a way to confirm that the star is going into the slit? Can we do a slight offset just to see the star and then put it back in the slit?
Sure, yeah, I can. I'll see something there. I was going to suggest a longer exposure.
Yeah, he's
Sure,
hoping
we could
to
do that
see
as
the
well.
faint
We should
star.
do that as well. And we're just
Right
getting
now-
to 18-degree twilight now.
Yeah, right now, that star's probably going through the slit, and we're not seeing it at all.
Perfect.
Move it a small amount.
1 arc second, you mean?
Yeah.
Let's do 2, just because the slit is 1 arc second wide.
So I do see something that popped off the slit there.
I don't see it.
So I'll go ahead and put it back on.
Okay, I did see it. I don't know. Did I miss it?
I think it's right above his cursor. If you look where the laser pointer is, there's a very faint smudge, I think. Maybe not, but he's circling where it should be.
I think I see that.
For some reason, I'm not seeing it. Okay, that's fine though.
Oh, just put it back on the slit. So
Okay, no problem. No problem. No, I didn't see it at any point. So, as long as you guys saw it, that's good.
we did.
I think
You
I
did.
see it just right at the
No, you don't need to. No. I completely trust you. No, thank you. Yeah, good time. Perfect time.
All you have at it.
All right, Yuting, go ahead. You got to do the honors. Hit the expose button. Yeah, okay, this is excellent. We've just started a sequence of 6 18-minute exposures. So 6 times 18 is 108. So this plus the slight overhead of time it takes to read out the detector, etc., will take us close to 2 hours. So Geronimo, you raised your hand. Please tell me, what question do you have?
Sure. I was gonna ask about the slits, because in the image from the telescope, I can see that there are several slits, and I was wondering, so you can ask them to switch from one slit to the other depending on the spectral resolution that you wanna get?
Exactly right. That's exactly right. So what happens is these different slits, only one of them is perfectly vertical, you'll notice. The others are slightly tilted. So they're actually part of a wheel, and you can rotate the wheel and bring the correct slit into the light path. So what determines which slit we want depends on the atmospheric conditions. Today, the atmospheric conditions are such that the seeing full width half maximum is about 0.7 arc second. And so we want to get all the light of the star, so we're using a 1 arc second slit. If the seeing were much better, if it were 0.5 arc seconds, we might use the slit to the right of that, which is a 0.7 arc second. These slits have different widths, and we get to select one, exactly as you said. Only one of them is in the light path. The others are actually, light is blocked. Only in one
Perfect,
case
thank
does
you.
the light go all the way through to the spectrograph. Yeah, that's a great question. Thanks.
Okay, thank you.
I'm going to ask Yuting to see. Yuting, would you be okay joining the other Zoom call?
Yes, sir. Just a second.
No, take your time. Take your time. Okay.
Yeah, I
I'll
have
stay
a
on this
comment
call.
to make
I'll
to
stay on both
Raja.
calls.
You can unmute us to Raja so he can hear us, and maybe raise our hand and he'll call on us.
And Michael, Rita, Arena, anytime you're more than welcome to come join us. I'm going to show. You're welcome to join on the other Zoom call at any point. So here I'm showing folks on my screen that tonight, shows you who's on the Keck I telescope tonight and who's on the Keck II telescope. So on Keck I, for each telescope, it lists something called an observing assistant. These are the person or persons who are on the summit of Mauna Kea, actually physically there. And so for the Keck II telescope, Arena and Rita are on the summit. Support astronomer is Michael, and he is in Waimea, not on the summit. And we don't have, neither telescope has a night attendant anymore, but we have someone who's we have a couple of people on on-call support. And then we have the science team here. So I'm the PI, the principal investigator of the science team. Joe Hinawi has time on the Keck I telescope. LRIS stands for low resolution imaging spectrograph. ADC is the atmospheric dispersion corrector. We are on ESI, which is a shell spectrograph and imager on the Keck II telescope. And Yuting Feng is the PhD student at UC Santa Cruz, who I've been talking to on the other Zoom call. He's going to join this Zoom in a bit. Doug Grion-Filio is a first-year PhD student. Yuting is a fourth-year PhD student. Doug is a first-year PhD student. Doug is on the East Coast right now, so it's very late for him. So he'll join a little later in the night when it's morning for him. Same for Eric Peng, who's a professor. He's on sabbatical at Harvard. He'll connect in the later part of the night when it's morning for him. And Emily Cunningham is a postdoc at the Flatiron Institute in New York. She's a former PhD student of mine at Santa Cruz, and she again will connect a little later. So the first part of the night, it'll be Yuting and myself. So Feng, GuhaThakurta, that's who it lists. And you can see things like sunrise, dusk, dawn, sunrise. If these times look unfamiliar to you, it's because they're in Greenwich Mean Time. You have to subtract 10 hours to go from GMT or Universal Time to Hawaii time. So sunset was 6:38 in Hawaii. So if you add 10 hours to that, it's 0438 GMT. That's what these times are. And then these times at the bottom are also given in, let me make sure of this. Yeah, these times at the bottom are also GMT times at the bottom. So 10 hours GMT is the same as midnight in Hawaii. That's sort of close to the midpoint of the night. Close to, not exactly the midpoint of the night. Okay, so I wanted to show you this screen. This is the spreadsheet that Yuting has put together to plan almost like a train schedule for the night, what we're going to do, sort of moment by moment. We are currently on this DES target, row 13. That's what we're on. This is what we spend 6 times 18 minutes on. We did 2 times 1-ish minute on each of the first 3 bright RR Lyrae. And when I say bright, I mean, you can see their magnitudes here, 13.3. These are closer to 21 or 22. This is the faintest one we'll observe tonight, is the one we're observing now, 21.7. Just to give you an idea, this is a logarithmic scale, an inverted logarithmic scale. So the human eye, the faintest star it can see is 5th magnitude. From a very dark place, the faintest star we can see is 5th magnitude. And these things are 8.5 magnitudes fainter than that. This is 16 magnitudes fainter than that. Every 5 magnitudes is a factor of 100. So when something is 7.5 magnitudes fainter, it means it's 1,000 times fainter than the, these are something like 10,000 times fainter than the eye can see, and these are more like 1,000,000 times fainter than the eye can see. Actually, let me calculate that again. 15.
Yeah.
No, our science stars are a little more than 1,000,000 times fainter than the faintest things the eye can see. And the brighter RR Lyrae are close to 10,000 times fainter. So 10,000 times fainter than the eye can see is considered bright by Keck, and 1,000,000 times fainter than the eye can see is considered faint for this kind of work by Keck. And this is another way of saying the Keck telescope is a giant eye that's much, much bigger than the human eye, much bigger. Okay, let's see who is on the call here. Yuting hasn't joined yet, so let me see when he joined. Oh yeah, okay, yeah, no problem, no rush, no rush. I'll introduce you when you join that call. I see a lot of people whose names I recognize from your sign up. Thank you for going through the registration form and signing up. Mariella, welcome. Would you like to say a little bit about Keck and outreach there? I'm putting you on the spot. Michael, I want to introduce you as well. Feel free to unmute, and I can also stop sharing my screen if people want to, so people can see you when you introduce yourself.
Aloha, everyone. I'm Mariella. I'm the communications officer here at Keck Observatory. Thank you for joining us. This is actually my first time also getting a sneak peek at Raja's night of observing here at Keck. So just a little bit about me. I handle communications, but I'm also involved in community engagement. So Shadow the Scientist is really important to me personally and to Keck in terms of our community outreach and education outreach. So mahalo everyone for joining. Good to see everybody.
Hello, Mariella. I didn't give you any warning and put you on the spot right there. So thank you. Thank you.
That's okay. Good to see you.
Good to see you, Mariella. Michael, do you have a moment to introduce yourself and say what your role is, please?
Sure. I'm Michael Lundquist. I'm a staff astronomer here at Keck, and I'm supporting the observations. So I'm here to make sure the instrument runs smoothly and that Raja gets the data that he needs tonight.
Thank you, Michael, for hopping onto this. I think this may be the first time we are working together on ESI. Is that right?
Yeah, the first time on ESI.
Fantastic. I was part of a team that helped design and build ESI at UCSC many years ago. So it's an instrument that's very, very dear to me. A beautiful instrument, really. Let's see. I see that there's a hand up from David at Griffith Observatory. David, would you like to ask a question?
Yeah, thank you, Raja. A couple of things. One, you noticed our YouTube stream has a delay, but the video and the audio are both delayed together. So you don't need to worry about them hearing things out of sync. It'll all work out for the folks there. But the question I had is, how is the telescope, of course I know the answer, but how is the telescope able to stay pointed at the right star for 6 18-minute exposures? That it seems like you'd have to have incredibly precise gears. Can you show us how that's done?
I'll share my screen for that, if that's okay.
Yeah, please.
Okay, so I'm going to share my screen. So back to seeing the instrument control instead of people. But right on this screen, right here on this screen in the upper right, you'll see that one of the stars has a little box on it. You'll see it now. You see a little green box on the star in the upper right. That star is what we call a guide star. That's a bright star, and its location, the location of its light on the pixels of the detector, are held rock steady as the telescope, as the Earth rotates and the telescope moves to compensate for that. The telescope is this giant instrument. It has, giant motors, etc. And yes, it's programmed to move to exactly compensate for the rotation of the Earth, but it's only so precise. This system here that allows the light of a star to become our guide, that is, we prevent the light of the star from drifting off the pixel it started on onto the neighboring pixel. When we see it starting to drift into the neighboring pixel, we adjust the rate at which the telescope is rotating ever so slightly. And that's really the system that's used for such precise tracking. Every pixel is a fraction of an arc second in weight. So we can centroid the light of the star to a fraction of a pixel. So typically this guiding accuracy is about 1/10 of an arc second or better when this happens. David, I don't know if that answers your question.
It does very well. Yes, thank you very much.
And I don't know if Michael wanted to add anything to that, or.
No, that was perfect.
I'm going to see if Yuting is on here. Yeah, Yuting, please go ahead, introduce yourself. Again, I'll stop sharing my screen briefly so people can see people as they introduce. So I'm going to gallery view here.
So yeah, it kind of feels weird, like I'm looking at myself on two screens, but yes. So I'm Yuting Fen. I'm currently on my fourth year under the advising of Raja, doing my research job as a PhD student here at UCSC Astro Department. And these stars, not all, but quite a few, these distant RR Lyrae stars are kind of like part of my main research program. Basically, we're taking spectra then to study the dynamics of the distant, very distant stellar halo of Milky Way, which is like very few people had did before, mostly because they don't have such well-determined distance for like these stars to know their velocities and stuff. So I consider that a pretty exciting project, and we have been using ESI for this project more than a
third semester, right? Doing this.
Yeah,
we started in 21.
We have been quite familiar with this instrument and how it works and stuff. But I guess and I hope it will be some new things and exciting stuff for you to see here tonight.
Fantastic. Yuting is being very modest. He has discovered the most distant RR Lyrae in the Milky Way galaxy, right? So the most distant ones are so faint that even Keck is not powerful enough for us to get spectra. But so we are going out to a distance of about 150 kiloparsecs, or 500,000 light years. That's how far out we can get spectra. But the most distant things he's found are more like 1 million light years away, or 300 kiloparsecs, more than 300 kiloparsecs. It's a terrific achievement. In fact, I took Yuting out to dinner the other night, saying, we got to celebrate this discovery. So we went out and had a good Chinese dinner the other night. I see a whole bunch of familiar faces on the call, so this is great. Pran, do you have a moment to introduce yourself? I'm totally putting you on the spot here.
Yeah, that's okay. Hi, Raja and everyone. I am Pran from the Republic of Kosovo, but I'm currently in San Jose in California. I do my master's in planetary science at UC Santa Cruz. So I am in the planetary science department, but I have been fully supporting this outreach effort that Raja has been doing. I think this is really great. We don't always get the opportunity to see how these large observatories are being operated. And I think this is bringing something really cool for us to see. So thank you, Raja, and to all your team for doing this. This is amazing.
Well, thank you, Pran, for all the amazing connections you bring to the research team and to the observatories. A moment ago, I see a chat from Paul from Mauna Kea. I don't know. I don't see Paul on the Zoom call anymore. Maybe, but I know there's a school from Mauna Kea that's connected, and there was going to be a bunch of students and teachers who are connecting. Mariella, this was from Vicky Newberry, is the teacher who contacted us and had arranged for a group to connect. through one Zoom link. I think they're going to be physically in one space connected.
So good to see Molokai on the call. Aloha.
Hi.
Aloha.
How are you?
Just
So,
fine.
update for you.
Really exciting for our students. Real quick. Hi, Leah, Ali'i, Azrael, and we have a few at home participating.
I'm here about 3 o'clock tomorrow.
We're beginners,
And
and we're
you
thrilled for this opportunity.
take the bag of whatever the stuff is out of the fridge about 3 hours before we're going to use it, so that it can.
I think we're getting some stray audio from someone here. If you wouldn't mind muting yourself.
3 hours before.
Around noon, and we also, we'll need one bag, and then we'll need, one set of, the liquids that we inject in.
Do they have to come out as well?
For now, let's do that, and we can, check with her tomorrow whether we should.
Okay, sorry about that. You folks from Molokai, thank you so much for joining. I can't wait to visit you in person. I will definitely come by. It's not enough to be on a Zoom screen, really. I would love to come visit, and I would love to. I'd love for you guys to come out to the Big Island as well.
That's a goal of ours, so thank you very much. I think we see next year as a year that we really would like to focus on space science, environmental problems in space. Really motivated by that, so thank you.
I've just added Arena and Rita. I've pinned your screen. If you wanted to introduce yourselves, that would be great.
Hi, everybody. I'm Arena. I'm Rita.
Yes. Hi.
So we're operators here. So I've been at Keck for about, I don't know, this is my 4th year operating here. And Rita's,
I'm just training up. So this is actually my very first night operating K2. So she gets to show me all of the things about it that are completely different from K1, which is what I've been dealing with over the past year or so.
Yeah, that's why there's 2 of us. Usually we get to be lonely vampires up here. It's just a couple of us here at the summits. I don't know if Raja mentioned this, but mostly we're responsible for the safety of the telescope. I would say that's the #1 priority. Making sure that snow doesn't get in the telescope. Fun things like that, so that we don't accidentally drive it where it's not supposed to. So we move the telescope through the night, making sure that Raja and anybody else can get their science done quickly and efficiently, kind of get us going on sky, and then I don't know.
I mean, that's basically all we're doing. We're not the scientist here. We're not the astronomer. We're just doing everything that they tell us to do and making sure that things go as smoothly as they can.
You're not just doing what you're doing. What you're doing is absolutely amazing. I've been on the summit of Mauna Kea, and I know how physically uncomfortable it is to be up at 14,000 feet, stay up all night. So I really appreciate the physical hardship you go through night after night to make this science possible on the telescope. It's no small matter. It really is a huge thing. So thank you.
Definitely something to get used to, but we like it. We like being up here, and actually being near the telescope and being able to do all of these things for you and for everyone. And we just have lots of coffee and survive the nights.
So we're pretty acclimatized too. I mean, we've been working up here for a while, so 14,000 feet isn't such a big deal for us as it is for everybody else coming to sea level. But also coffee.
For a little while there, I had noticed, maybe a couple of years ago that there was sort of OAs were standard using oxygen. Is that something that is pretty common or not so common?
Depends. So we have oxygen available, and if we feel like using it, then it's easy to use. And I know some people prefer it. I kind of don't like it because it dries out my nose and everything. And so I typically don't use it, but it is definitely helpful to have up here.
Yeah, everyone's really different. Some of us need a little more help up here than others. But most of the time we're sitting and we're not doing a whole lot, as opposed to our day crew who run around the entire telescope up and down the stairs all day, every day. So I think for them it's a little more exercise, whereas we tend to be a little more quiet here and we try to conserve our oxygen.
No, I really appreciate it. Again, it's so physically demanding to be on that. I mean, for me, when I come out to Keck and I go out to the summit, it's a combination of three things, right? It's sleep deprivation, jet lag, and oxygen deprivation. And I can tell you that combination is no fun. So no, it's thank you. I really appreciate that for everything you do. I know that we just had a long exposure readout. So what I'm going to do briefly is share the screen again so that we can see what, compared to those bright RR Lyrae that we were getting spectra of, this faint one, even though we spent 18 minutes on it, not just 1 or 2 minutes, I can bet its spectrum is going to be very hard to see. So I'm just going to go there for a second. So here's that spectrum, and you're probably wondering where, because all you're seeing is what looks like the barcode symbol of a grocery store item, but there is a spectrum here, and let's see if we can display it any better. There we go, can see it. So it's a very faint spectrum. So I'm going to zoom in so you can see it a little better. Let me zoom in. There you can see it. It's very faint. It's this very faint streak. That's why we're taking 6 exposures. And if we find that even that is not enough to measure a velocity for the star, we may come back and take more. I'm going to zoom in a couple more times, actually. It's clearly there. The continuum of the star is clearly there. You can see it in all the orders. This one, this order, this one, this one. And if I move over a little bit, you can see it in literally all of the orders. I'm just panning across. In the reddest order, the one that's furthest to the right, you can barely see it. And with a little bit of squinting, maybe it's there. Second last one, it's definitely there. Third last, it's definitely there. Fourth last, fifth, sixth, seventh, and 8th. There should be a total of 10 orders. 9th, it's almost lost, and I don't see it in the 10th one. So this is what it means to find and study a distant RR Lyrae. This is why it's so boring. When we get to these faint science targets, we have to spend 2 hours with the world's most powerful spectrograph telescope combination to even measure a measly velocity for this star. That's all we're trying to measure, not chemical composition or anything like that. That would be even more challenging to do. We're just trying to get a velocity, a Doppler shift. And let's look at the control screen one more time. We're on the second exposure. That's why it says exposure 5 instead of 6, because we're on the second one. And you can see that the time remaining is something like 12 minutes. And the time that's elapsed is a little more than, it's almost 6 minutes. So these two, the number that's counting down number that's counting up in the upper right, and the number that's counting down here, they add up to the total exposure time of 1080. These are the different, this thing that's called, what's it called, dashboard, is a cartoon of the physical instrument. This blue arrow represents light. It comes in through the slit. We're on the 1 arcsecond wide slit. The deca controls how long the slit is, controls the length of the slit, I believe. This is a slot for a filter. This is the grating, the echolette grating. ESI spectrograph actually uses an echolette grating and a prism. The prism does the cross dispersing. It separates the different orders. This controls the focus setting, and then this green box represents the camera, the CCD detector, and where that sits. What I'm going to do is go back to, so I can see the participants in this window and see if I can call on, did the Akaula school in Molokai, did you want to say anything more about your school and this connection. You connected to us through Ohana Kilohoku, I assume, but I'm also going to see if anyone else from Ohana Kilohoku is here. I don't see Sam. Again, I don't mean to put anyone on the spot, but if anyone wishes to ask questions or speak up, introduce themselves, or I know we have. I'm delighted to see you here, Mariam. I know you're connected from Western Iran. So thank you for being on this call. It must be very early in the morning for you.
What do we say? Just a little bit more from Akula School. We are an environmental education-based school, but it's always been terrestrial, and it's really been focused on local issues, Hawaii-based, mostly even Molokai-based. And this year we were challenged by Dr. Morba Job to see what we could take from what we've learned in those investigations and how we could apply it to issues in space. And it just exploded into a much broader picture of interest and inquiry, way beyond just looking at space junk or space tourism, but actually trying to understand the whole picture beyond a bigger picture, and more opportunities for our students, many of whom are interested in aviation, and some of whom have always really been interested in what I call spectator astronomy, perhaps. So this is kind of an open door for us that we're looking at traveling through.
Oh, thank you for sharing that. Today, you're really learning about the galactic environment of the sun and solar system. Very much about the you can call things home on different scales, right? Your school is, in a sense, an academic home. The island is a home on a bigger scale. The island chain of Hawaii is a home on an even bigger scale. The world is a home on an even bigger scale. And in this case, we're looking at a home on the Milky Way galaxy scale. It is very much about our environment still. No, thank you for connecting. I really appreciate it. I know it's not, and there are many better things to be doing on a Friday evening than staring at a bunch of nerds like us looking through, not looking through a telescope quite directly, but looking at the silicon devices that collect the light from these telescopes on our computer screen. But I appreciate your spending the evening with us.
I had a question, Raja, back here from Griffith again.
Yes, please.
I know that these stars are about the same magnitude, at least in the G band, as the stars we observed in Andromeda in the I band, but we used LRIS. Are you using ESI because these are bluer and it's capable of hitting them, or would LRIS Blue be able to do any of these stars?
LRIS Blue would be able to do these stars. The reason we're not using so the advantage of LRIS Blue would have been if we could have observed multiple stars at once. But these stars are so sparse in the sky that we can only get one at a time. And then the advantage ESI has over LRIS is slightly higher spectral resolution, and we get the entire spectrum at once.
Mm-hmm.
That's the reason for using ESI over LRIS.
Yeah, that makes complete sense. Thank you.
And David, these stars are actually, in a way, they're brighter than the Andromeda stars. The Andromeda stars were in the I magnitude, they were 21. These things are V magnitude of 21. The V minus I stars of the Andromeda objects were about 1.5 to 2. So those were their V's got as faint as 22.5 and 23. Of course, we were taking spectra in the I band, so that's what mattered. Yeah. And here we're taking spectra of H alpha, which is more like the R band and shortward. These things hardly have any calcium triplet. As you said, these stars are hotter, and that washes out a lot of the absorption lines and makes them very difficult to study. Mm-hmm. They're not as hot as stars get. There are, as you saw in that color magnitude diagram, there are blue horizontal branch stars that are hotter. main sequence stars that can be hotter. These are not as hot as stars get, but they still have very washed out. The combination of them being chemically anemic and having high temperatures makes their spectra very difficult to study. There are really very few features.
And I'd imagine the gravity is a little higher on these, which would tend to spread the lines out a bit.
Gravity is indeed a little bit higher because they're more compact for a given mass. They're the same mass as the sun, but they're a little more. They're a little lower mass than the sun. They're 0.8, maybe, the mass of the sun, but they're significantly more compact. They've lost some of the outer envelope. You're sort of seeing the hot core.
Yeah, so folks, they're more compact than a red giant.
Yeah,
which is more
I'm really falling in love with RR Lyrae now. It's so beautiful.
Would there be any advantage to observing these with the James Webb Space Telescope?
It would have to be one star at a time because they're so sparse in the sky. What has made real progress in this field are wide field imaging surveys. So what Yuting used to discover these was a 100 square degree survey with the Canada-France-Hawaii telescope on Mauna Kea. The dark energy survey used a telescope in Chile to cover, I think, 5,000 square degrees. Pan-STARRS covered a third of the sky, 30,000 square degrees. So it really takes sky coverage rather than, it really takes sky coverage to discover these stars. James Webb might be able to get spectra of these stars, though, of the faintest ones. I'm very grateful to my colleague at UC Santa Cruz, a grad student at UC Santa Cruz, Cesar Rojas Bravo. Cesar is from the University of Costa Rica, and he connected us to an organization called Alpha Sen, which is a STEM outreach organization, an astronomy outreach organization that's based in Central America, and they've become a formal partner of they've become a partner. There's nothing formal about Shadow the Scientist, but they've been a partner of Shadow the Scientist. And through Alpha Sen, we have many participants in today's call. A shout out to Pran's organization, Astronomy Outreach of Kosovo. Shout out to Ohana Kilohoku, that Sam King leads. None of our work, our outreach work, would be possible without our partners. The partner organization that have these amazing networks of students and educators, they've built a relationship of trust with these networks. They're an integral part of Shadow the Scientist. And I'm hoping that Griffith will be a partner. Griffith Observatory will be a partner.
We still have 65 people on our YouTube stream watching what we're doing here. So that's quite a success. Throughout the main show, we usually have anywhere from 150 people. It varies. So to still have 65, at 10:18 p.m., it shows we're really on to something here. People want to know what it's like when astronomers do the work, what it really is like to run an instrument. So thank you very much for making this possible. It's really something special.
Thanks, David. I think it's the authenticity of it. It's not curated content, right? It's not something that we're doing specially because there are others who are connected on the Zoom call. Yuting and I, and Arena and Rita and Michael, we'd be doing this work anyway. Whether or not that's the key thing here. It's really authentic. You're seeing the actual work we would have been doing with or without you. Let's see, I do want to go and so in 90 seconds or in a minute and a half, the second exposure will read out. And this time I'm going to zoom in so you can see what happens when the second exposure reads out. So you'll see that if I zoom in here, I'm going to go to normal first, center. Normal means zoom of 1. Then I zoom in. you'll notice that there is a zillion of these very bright spots. These are high energy particles from space called cosmic rays that strike the silicon detector and release electrons. And the silicon detector can't tell them apart from light. They just know that electrons have been released by something. And so we take multiple exposures so that we can do anti-coincidence. So in the second exposure out of the 6, these cosmic rays will be in different locations. And you'll see that in a matter of a few seconds, in like half a minute, when this thing reads, when the time remaining on this goes to 0 and it reads out the second exposure. So I'll switch screens at that point. So you'll see how the cosmic ray spots will change. And this is the anti-coincidence we use to reject the effect of cosmic rays. Sorry.
And by anti-coincidence, folks on our YouTube stream,
I
he
know
means
this is,
that
we're
cosmic
down
rays
to
hit
10,
different
9,
spots.
8, 7. This is exposure 2 of 6 that is about to finish. So I'm going to switch screens now.
Exposure complete.
And please pay attention to this part of the screen, the upper part of the screen, upper left part of the screen. And you'll see that as the new exposure sweeps down, you'll be able to tell because the cosmic rays will change. There you go. You see it's happening right now. New cosmic rays appear where old ones were not, and old ones disappear. So this is the second exposure, and thankfully, the star that we targeted, its continuum is still visible. You see this. It's not quite vertical. It's like an arc. I think of reading an ESI spectrum like
DCD readout complete.
Almost like reading a script that's written from top to bottom, and then top to bottom, scroll over one to the right, or shift one to the right, top to bottom, etc. This is how you read the ESI spectrum. Yuting, I will say that, yeah, sorry, go ahead, please.
Oh, sorry, I just wanted to ask, for perspective on like the range of the spectrum, what are the, like, more or less, what is the range of wavelengths that we're dealing with here? Like from
That's a great question. Let me zoom out and give you that information. We are going from about 3,900 angstroms, so 390 nanometers on the upper left part of this display, to about 1.0 microns, so 1,000 nanometers, 10,000 angstroms in this part, in the lower right part of the array. So the last of the orders, these are called orders, these curved bands. These are called orders. So this is, I believe this is order 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. ESI has orders 15 to 6. 15 is the shortest wavelength, 6 is the longest wavelength. So it goes from about 390 or 380 nanometers to about 1,000 nanometers. Does that answer your question about wavelength range?
Yes, absolutely. So it's like full in the visible range and plus a bit of IR?
A little bit of IR, a little bit of UV as well. I mean, the rainbow part of the spectrum pretty much goes from about 4,000 angstroms or 4,500 angstrom even to about 7,500 angstrom. That's the part the eye can see. Or, I'm using angstroms and nanometers interchangeably. I apologize for that. So something like 400 or 450 nanometers to 750, 800 nanometers is what the eye can sense. Yeah, so we see a little of UV and a little bit of IR on either side of the full visible spectrum. You think, will we ever be able to pull a velocity out of such a faint spectrum? Will we ever be able to pull a velocity out of such a faint spectrum?
Well, as long as we can see it, I think it's extractable, but
What was the last thing you said? Yeah, bluest and reddest orders we can discard. There's no information there anyway. If needed, we could come back and boost the exposure by taking more exposures in the same phase of the star on another night.
I bet they'll be able to get a
Yeah.
velocity out of these. I've seen worse data, and they're taking 6 images. So imagine
No,
you're
no, it
gonna
has to be extractable. I
more
agree, but
light,
in terms of
but you
getting
also
enough
get
signal
more
to noise
noise.
at H alpha,
Noise gets
other absorption
down to the
lines.
square root of it. So
See, this is
signal to noise doesn't
I'm
quite go
reassured
up
by one thing:
linearly
the fact that
with
we
the
could see the
exposure time.
spectrum, and that it's at the faint end of the things we study, makes me think that this is a normal star. It's not a quasar that's faded or brightened. Yeah. One of the main contaminants we run into, folks, when we're trying to study distant RR Lyrae, is we run into these things called quasars that are much further away, but they look as faint as these distant RR Lyrae, and they also fluctuate in brightness, but their pattern of fluctuation is not periodic. It's not strictly repeatable. And sometimes if you don't have enough measurements, one can get confused for the other. But a spectrum can tell us whether it's a contaminant or a real RR Lyrae. So that's another reason to take a spectrum. We can confirm that it's indeed an RR Lyrae and then also measure its velocity. All right, let's see other questions. People are welcome to ask questions from the Zoom room, please. This is a great time to ask questions. We are, as you can see, we're now in the third exposure. I'm going to close this for a moment. We're in the third exposure. So that's why it says number 4 here, because it's finished exposure 6, finished exposure 5. It's now on exposure 4. And it is not quite halfway through. It's only finished 5 minutes of the 18 on this one. This is how boring a good night is. If everything is going well, really, as astronomers, we get to catch up on other work during the night. We get to check our email. We get to write our next proposal for more telescope time and things like that. But if, touch wood, the night is going well, the sky is clear, the seeing is good. I don't know if we have any good seeing check right now for the, do we think the seeing is still about 0.7 or 0.8, or is it better / or worse?
So when Raja is talking about seeing, he means how stable the atmosphere is over the island. So if it's very stable,
is there a way to tell from the Keck guide?
Small points.
Flavio, your question is this system used in the observatory? Which system did you mean? You mean the spectrograph being used here?
Yeah, the one that you're screen sharing right now?
Yeah, so I would say it's not the most modern because ESI was built a couple of decades ago. There are more modern spectrographs, but they're not necessarily better for the work we're doing. Some of the modern spectrographs that have been built, there's a new infrared spectrograph that's been built since ESI. For this work that we are doing, it's one of the best instruments in the world. Not just at Keck, it's one of the best instruments in the world. And Flavio, I'm really glad you got to join and take part.
No, thank you, and to Ms. Faber for inviting me and having me in this meeting.
Oh, that's great. Are you at home now in California?
Yeah, I'm home right now. I just made it right now, but I've been on the meeting since like the beginning. I just I had to see it somewhere else.
No problem. I'm really glad you're joining.
Hey Raja, maybe you have mentioned this already, but what is the spectral resolution?
The spectral resolution for ESI is it's between 5 and 10,000. Okay, so it's several thousand. What I mean by that is if you take the wavelength and you divide that by the wavelength resolution, lambda divided by delta lambda, that's something like 7,000 for ESI. And a good way to think about it is if it, let's say, if it were 10,000, or whatever the resolution is, if you take the speed of light and divide by that, that's the velocity resolution we have. So in other words, if it were 10,000, you divide the speed of light, which is 300,000 by 10,000. Yep. A little bit, but Michael would know more than I would about this. Michael, what do you think?
Folks, I didn't quite hear what they're talking about, but they could be talking about maybe refocusing the telescope. Keck does need refocusing periodically throughout the night. So
we're in the visible, yeah. It depends on how, do you think it would really ruin the spectrum?
If there's a laser going right through the star, absolutely.
Okay.
If the laser is nowhere near us, then no. But I don't know
where they're pointing.
I don't know where that is.
Yeah.
Yeah, so keeping in mind that you would have the sodium in your spectra, like if that
they could be worried about a cross beam if Keck I is using adaptive optics.
It would. We are trying to measure the sodium doublet in these stars. We are trying, that's one of the, you saw in that star that it was the H alpha sodium doublet. These are absorption lines we use to measure the velocity.
It sounds like they're worried about a laser being close to their field of view.
Sorry. Okay. Oh, good. Okay. Good. Okay. I'm going to explain to the folks on the Zoom call what this was, and please correct me if you hear me say something that's not accurate. So we just got something from the Subaru telescope on Mauna Kea. They're doing some engineering studies on their telescope tonight, and they're using a laser. And where they were going to point the laser would have interfered with where we are pointing the Keck telescope, and they asked us if they could get an override from us, that is, if they could get permission to point the laser. And we said no, because we're trying to take a spectrum of a very faint star. We could lose these 2 hours of precious Keck time if one of our 18-minute exposures or one or more of the 18-minute exposures were had this sodium glare, the human-made sodium glare, was interfering with the astronomical signal of the faint RR Lyrae. So this is one of the downsides of having more than one telescope on the same summit. But of course, the summit of Mauna Kea is one of the best places on the surface of the planet to observe the heavens. Just the conditions are so perfect.
What are you guys going to be looking at today?
We are looking at these stars, individual stars that are very far away from us, a class of stars called RR Lyrae. These are pulsing stars. They pulse in brightness. They change brightness periodically. That's what we're studying today. They are quite special, these stars. They're special. They're easy to find because of their characteristic way of pulsing. But they're also easy to tell distances too. Unlike many things in astronomy, when we look at RR Lyrae stars, we have a very good sense of how far away they are. Does that answer your question about what we're looking at today?
Yes, thank you.
Thanks. Yuting, I'm looking at this in the magic window. I'm looking at the seeing And it's actually significantly worse than an arcsecond. That's what I'm seeing. I don't know if that's how that relates to the actual seeing on Mauna Kea, at Keck right now. I see a question on the chat. Let me pull that up. Yeah, sure. David, I assume this is okay. The question is, can I ask a question from your presentation earlier on All Space Considered? You mentioned that there are stars associated with the Milky Way halfway to Andromeda. Do we know what the spatial distribution of those stars are? Is it a sphere or more of a disk? We think it's a sphere. We don't know for certain yet. The reason we think it's a sphere is different groups who are surveying the sky all around us, in all possible directions, are seeing consistent things. That suggests it's not a disk. It suggests it's a sphere. We're not quite at the center of the sphere, but the sphere is so much bigger than our offset from the center of the sphere. As you saw, the sphere is 40 times bigger. The radius of the sphere is 40 times more than 40 times larger than our distance from the center of the sphere. So we do think the distribution is RR Lyrae that people are finding, not just us. I think based on Yuting's study alone, we can't tell that it's a sphere. But by comparing his study to that of other people's studies, I think we can safely conclude that we are seeing a spherical distribution, or close to spherical distribution of RR Lyrae. I'm sure there are lumps, and it's not a smooth sphere. I'm certain it's not, because we are seeing sort of the at these distances, we're seeing sort of the cannibalism history of the Milky Way, these sort of partly digested satellite galaxies, partly digested smaller galaxies that have been cannibalized by the Milky Way. But it's closer to a sphere than a disk. Jim, if that, I don't know if that answers your question. Sorry, this is JIMREA from from All Space Considered.
Yes, that's right. I've been watching the live stream, but I had signed up for the Zoom, so I jumped on to ask that question.
Thank you. Did that answer your question?
Yeah, pretty much. And thank you for doing this. I'm actually not with the school, but I saw the sign up on Twitter. I watch All Space Considered every month, and this is just so exciting.
Thank you. I'm a huge fan of All Space Considered, as David knows, a huge fan. I wouldn't have been on it 3 times otherwise. And so
I don't have anything to do with it other than being a big fan myself.
Good.
We thank you both for being big fans of the program. And I'll take the time now to say we are going to sign off in the near future. We have folks up at the observatory that need to get home. And we're reaching our time limit here. But this has been absolutely fascinating and just a great experience to be able to see. It's making me want to go observing again, Raja. It's kind of
you have to do it, David.
It's habit forming. So we'll talk, and
okay.
Maybe we'll come up with some fun things to do and go on a Keck run. And also, we look forward to joining you on a Lick run at some point. I know that you're doing these from the 3 meter there, and it's just fascinating to see all this work and see everybody excited about what's happening. So thank you again. And from Griffith Observatory, just have a wonderful rest of the night tonight. We wish you clear skies and steady seeing and continued luck with the observations. So thank you so much.
Thank you, David. Thank you so much for hosting me. Thanks to you, Katie, Michael, for hosting me. I really appreciate it.
Yeah, absolutely. And we look forward to having you back again sometime in the near future, and we'll talk soon. I want to hear more about these observations you're taking and where it's leading. And good luck to your student here and everybody that's helping with this. This is really a fantastic project. Very, very exciting.
All right. Take care.
So thank you all, and we will check back with you later. But thanks, everyone. We're going to end our stream now, and have a wonderful night, everybody. This has been a wonderful experience. So thank you for joining us.
And the YouTube stream is going to end, but we're going to stay on Zoom for a little bit longer. Well, Yuting and I will stay on all night, but folks, I know it's well past
Exposure
the 90-minute point that we set for Shadow the Scientist. So when folks need to disconnect, you feel welcome to. You're welcome to, of course. But yeah, this has been terrific. I'm really glad so many people connected and we got to answer and talk about so many things today.
Thanks everybody for joining us again tonight. It was a really wonderful experience to end this with Shadow the Scientists. Just fascinating to watch a Keck run happening live. This is what I did for quite a long time when I was going observing. You saw what it is like on a good night where things are working well. Nobody was overly panicking and things were working pretty well, but that's what it's like. That's actual data rolling right off the telescope of stars that are 1 million times fainter than the faintest one you can see with your naked eye. Which I just want to point out one thing if you're still here with us. This is why astronomers are going crazy about those constellations of satellites. They love to say, well, we're going to make them fainter. They'll be too faint for you to see with your naked eye. And I say, I'm still looking at things with telescopes that cost, I forget if it's $10 a minute now to operate this, or if it's 20, I forget the exact number, if it's up to $100 a minute when you operate Keck. But you're ruining exposures if you have these things that are 1 million times brighter crossing your field of view. It's just crazy. So we are studying very faint things with very big telescopes, and it was just a pleasure to be able to see it. And again, thank you everybody for joining us on the chat. It was great fun, and we'll be back on April 1st, no joke, and for another episode of All Space Considered. So thank you so much, and thank you Matthew and Caitlin for sticking it out up there at the observatory. We really appreciate you staying there late so we could enjoy this wonderful experience. Good night, everybody.
Good night.